Our universe, a vast expanse of boundless wonder, is brimming with secrets and enigmas that have confounded humanity for centuries. From the infinite stretches of space, alive with galaxies, stars, and planets, to the colossal forces that govern the very essence of reality, the universe holds mysteries far beyond our comprehension. Join us on a journey through time and space, where we'll unravel some of the most mind-boggling phenomena that lie in the depths of the cosmos. Our story begins at the dawn of everything, an event that marked the birth of space and time as we know them, the Big Bang. Occurring approximately 13.8 billion years ago, this monumental explosion set in motion the universe's expansion, transforming the void into a dynamic, ever-evolving cosmos. In those earliest moments, the universe was an unimaginable furnace of heat and density, a seething mass of energy. Yet from this searing chaos, the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces began to take shape. In the blink of an eye, the universe expanded at a mind-bending pace, cooling rapidly, setting the stage for the first particles of matter to form. As the cosmos cooled, quarks and electrons emerged, giving birth to the building blocks of all matter. These particles soon combined to create protons and neutrons, the nuclei of atoms, but the universe was still far too hot for these protons and neutrons to bind into full-fledged atoms. It wasn't until about 380,000 years after the Big Bang that the temperature had dropped enough for these nuclei to come together and form the first atoms, mostly hydrogen and helium. This moment, known as nucleosynthesis, was pivotal in shaping the chemical landscape of the universe. Hydrogen, the most abundant element, and helium, its closest companion, were the dominant products of this early chemical process. In minute amounts, lithium also formed, marking the beginnings of a vast and complex cosmic chemistry that would eventually give rise to stars, galaxies, and planets. As the universe continued to expand and cool, gravity began its slow and deliberate work, pulling together vast clouds of hydrogen and helium gas, setting the stage for the birth of the first stars. These primordial stars, shining with the fire of nuclear fusion, played a crucial role in the unfolding drama of cosmic evolution. Deep within their cores, these stars forged heavier elements like carbon, oxygen, and iron. And when these stars reached the end of their lives, many exploded in brilliant supernovae, scattering these newly formed elements across the universe, enriching the cosmos with the materials needed to create even more stars, planets, and perhaps even life itself. One of the most profound relics from this ancient past is the cosmic microwave background, CMB radiation, a faint, almost imperceptible glow that permeates the entire universe. This glow is a remnant of the early universe, a snapshot of the cosmos just 380,000 years after the Big Bang. Discovered in the 1960s, the CMB became a cornerstone of modern astrophysics, offering compelling evidence for the Big Bang theory and providing a glimpse into the universe's earliest days. The CMB is not merely a faint afterglow of the universe's birth. It is a rich trove of information about the cosmos's infancy, revealing its composition, structure, and evolution. The radiation, cooled over billions of years as the universe expanded, still holds clues to its early conditions. What's truly remarkable about the CMB is its astonishing uniformity. Across vast stretches of space, the temperature of this radiation remains incredibly consistent, around 2.7 Kelvin, or nearly absolute zero. However, within this uniformity lie tiny, almost imperceptible fluctuations. These subtle variations in temperature are of profound significance. They are the cosmic seeds from which galaxies, stars, and ultimately life itself would blossom. These minute fluctuations are the foundational structures upon which the universe's grand architecture was built. By studying these temperature variations, scientists have uncovered a map of the universe's early history, one that shows a cosmos dominated by hydrogen and helium, the simplest elements that were forged in the aftermath of the Big Bang. This primordial composition aligns with our theories of nucleosynthesis, which predict the formation of these elements in the universe's infancy, offering yet another clue about how our universe came to be. And so it begins, our journey into the deep, ancient universe, where clues about its birth and evolution are hidden in the most delicate of imprints. The polarization of the cosmic microwave background (CMB) light is one such fingerprint, akin to the way polarized sunglasses block out glare by aligning light waves. This subtle distortion in the light reveals a wealth of information about the universe's infancy, offering us a glimpse into events that occurred in its first moments. The polarization patterns within the CMB are thought to be the echo of gravitational waves rippling through the nascent cosmos, providing indirect but compelling evidence for the theory of inflation. Inflation, a hypothesis suggesting that the universe underwent an exponential expansion in its first fleeting moments, offers a solution to several mysteries. It explains why the universe is so homogeneous on large scales, smoothing out any initial irregularities and shaping the cosmos into the structure we observe today. But that's not all the CMB has to offer. It also opens a window into the most enigmatic components of the universe: dark matter and dark energy. Together, they account for the majority of the universe's mass energy content, yet they remain largely invisible to direct observation. The CMB's interaction with matter over cosmic timescales helps cosmologists map out the influence of dark matter, which pulls matter together, and dark energy, which drives the universe's expansion at an accelerating pace. These invisible forces are the unseen hands guiding the evolution of the cosmos. But in the aftermath of the Big Bang, the universe was a formless, energetic expanse, primed to undergo a series of transformative phases that would eventually bring forth the structured universe we know today. This transition from the chaos of a hot, dense soup of particles to the ordered cosmos we observe was dictated by the emergence of the laws of physics. In those earliest moments, the temperatures were unimaginably high, and all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. As the universe cooled, these forces began to separate, setting the stage for the universe's grand development. The first to split was the strong nuclear force, the force that holds atomic nuclei together. This momentous event paved the way for the formation of the universe's first subatomic particles, quarks and electrons, just a fraction of a second after the Big Bang. As the universe continued to expand and cool, quarks began to bind together, forming protons and neutrons, the essential building blocks of atoms. This era, known as the quark epoch, was crucial in determining the types and amounts of matter that would dominate the cosmos. After this came the electroweak epoch, when the electromagnetic and weak nuclear forces split apart. This differentiation played a vital role in the creation of particles and antiparticles, and in setting the stage for the dominance of matter over antimatter. Without this asymmetry, matter and antimatter would have annihilated each other, leaving the universe devoid of the galaxies, stars, and planets that eventually came to define it. As the universe cooled further, around 380,000 years after the Big Bang, it reached a critical threshold. For the first time, temperatures dropped low enough for electrons and protons to combine and form neutral atoms. This phase, known as recombination, was a pivotal moment in the history of the universe, allowing photons to travel freely through space, resulting in the formation of the CMB, the first light to reach us from the universe's infancy. At this stage, the fundamental forces, especially gravity, began to shape the large-scale structure of the universe. Gravity's pull started to gather matter into regions of higher density, leading to the formation of the first stars and galaxies. This gravitational clustering continues to influence the cosmos, leading to the creation of galaxy clusters and superclusters, vast networks of galaxies held together by the invisible hand of gravity. Over billions of years, the interplay between these forces, the strong and weak nuclear forces, electromagnetism, and gravity, guided the evolution of the universe, from its hot, dense beginnings to the vast and complex cosmos we observe today. In the hearts of stars, elements were forged, and upon their explosive death throes, supernovas scattered these elements into space, enriching the interstellar medium with the raw materials for new stars, planets, and eventually life. Thus, the laws of physics, emerging in the wake of the Big Bang, didn't just dictate the behavior of the universe's fundamental particles. They guided the evolution of the universe from a state of simplicity to one of complexity. And with each step, the universe's intricate tapestry unraveled just a little more. Now, As we turn our attention to galaxy formation and evolution, we enter a realm where the influence of gravity is felt most acutely. Galaxies, those vast collections of stars, gas, and dust, are the building blocks of the universe's grand structure. Their formation and evolution provide a stunning insight into the dynamic dance of matter, shaped by the gravitational forces that continue to mold the universe, ensuring its expansion and the formation of the stars and galaxies that light our night sky. In this ongoing cosmic ballet, the forces of nature continue to choreograph the unfolding story of the cosmos. The story begins over billions of years, tracing the universe's origins and the subtle fluctuations that followed the Big Bang. These tiny variations, imprinted in the cosmic microwave background radiation, set the stage for the vast cosmos we explore today. From the earliest moments, the universe was a chaotic yet beautiful mix, an almost uniform field of matter punctuated by slight overdensities. Though these early deviations were small, they held the potential for everything that would follow. And so, under the inexorable force of gravity, these regions of higher density began pulling in more matter. Slowly, relentlessly, they grew. As gas and dark matter, the mysterious substance that doesn't interact with light but exerts a gravitational pull, were drawn in, they collapsed inward, forming the invisible halos of dark matter. Around these dark matter halos, visible matter began to gather. Gas clouds, once scattered, became denser and hotter as they compressed, eventually reaching the conditions necessary for the birth of stars. Thus, the first galaxies emerged, humble, small, and far simpler than the grand structures we observe today. These fledgling galaxies began their own evolution, interacting with one another in a chaotic dance. Some galaxies collided, merging into larger systems, while others were torn apart by powerful gravitational forces. This era, marked by frequent cosmic collisions, spurred bursts of star formation, known as starbursts, which reshaped the galaxy's very structure and their composition. As time passed, the galaxies continued to evolve both externally and internally. Stars, each with its own life cycle, played a key role in this transformation. Some stars lived fast and died young, burning through their nuclear fuel in a flash before exploding in supernovae. These violent deaths scattered heavier elements into the galaxy, enriching the environment and laying the groundwork for the formation of new stars and planets. In this way, the galaxies were constantly rejuvenated, each new generation of stars built upon the ashes of the last. Meanwhile, at the hearts of most galaxies, supermassive black holes lay hidden. These titanic entities, ranging from millions to billions of times the mass of the Sun, became critical players in shaping the galaxies around them. As they accreted matter, they released vast amounts of energy, which influenced the stars and gas clouds within their galaxies. The black holes were not passive observers of cosmic evolution. Their gravitational forces steered the motion of stars and gas, fundamentally altering the galaxy's structure and dynamics. But their impact extended beyond gravity. As material spiraled into a supermassive black hole, it heated up to extreme temperatures, emitting radiation across the electromagnetic spectrum, from radio waves to X-rays. This intense radiation had far-reaching consequences. Most significantly, it regulated star formation within galaxies. Known as feedback, this process saw the energy released by the black hole push away gas clouds that would otherwise collapse into new stars, preventing overproduction of stars and altering the galaxy's future. Through these processes, gravitational accretion, supernova explosions, and black hole feedback, the galaxies grew and evolved, their shapes and sizes telling the stories of their origins. Some became spirals with rotating disks and elegant arms, while others became ellipticals, stretching from nearly spherical to elongated ovals. Irregular galaxies with no defined shape revealed the chaotic nature of cosmic evolution. In this grand tale, supermassive black holes emerge as the architects of the cosmos. Not mere oddities, they are central to the narrative of galactic evolution. They shape not only the galaxies themselves, but also the very stars within them, leaving their mark on the entire universe. The balance of cosmic forces is more fragile than it seems. Supermassive black holes, with their immense gravitational pull, play a central role in the evolution of galaxies. This feedback mechanism, which can regulate star formation, can also freeze the growth of a galaxy. A delicate dance unfolds here, When too much activity is driven by the black hole, it expels gas from the galaxy, preventing the formation of new stars. But too little activity can lead to a runaway process where star formation goes unchecked, altering the galaxy in profound ways. What's truly fascinating is how the growth of black holes is intertwined with the very nature of the galaxies they inhabit. Observations reveal a fascinating correlation. The mass of a supermassive black hole appears to align with the properties of its galaxy's central bulge. This dense core of stars reflects the intricate relationship between a black hole and its galaxy. It's as if both are evolving together, with the black hole's feedback mechanism, through cycles of gas accretion and star formation, acting as the regulator of this cosmic relationship. But black holes don't just keep star formation in check, they are also sculptors of galactic structures. Jets of material, expelled at near-light speeds from actively feeding black holes, carve vast cavities in the intergalactic medium, reshaping the distribution of gas and triggering the formation of galaxy clusters. These black holes are much more than passive observers. They are active participants in the cosmic ecosystem. As galaxies merge, a frequent event in the ever-evolving universe, their central black holes eventually collide and merge as well. The cataclysmic release of energy from these collisions sends ripples across the fabric of space-time, creating gravitational waves. These waves, though invisible to the naked eye, carry crucial information about the fundamental forces of the universe and the violent processes shaping galaxies. Now let's shift focus. Stars, those fiery beacons in the cosmos, tell a story of transformation and creation. Their life cycle is not just a tale of their own existence. It is woven into the very fabric of the universe, influencing the birth of new elements, the building blocks of everything around us. The journey begins in the cold, dark clouds of interstellar gas and dust, regions of potential waiting to be ignited. In these nebulae, pockets of gas collapse under the weight of gravity, heating up as they draw in more material. Once the core of the collapsing cloud reaches the right conditions, high density and temperature, nuclear fusion kicks off and a new star is born. It's in this moment that a star enters the main sequence phase, where it will spend most of its life maintaining equilibrium between the outward pressure of fusion and the inward pull of gravity. How a star ages and ends its life depends on its mass. Stars like our Sun, which fall into the medium category, expand into red giants once they exhaust their hydrogen. As they begin to fuse helium into heavier elements like carbon and oxygen, they shed their outer layers in a stunning display, creating planetary nebulae. The remaining core, now a white dwarf, continues to cool and fade over billions of years. But for the massive stars, the journey is much more dramatic. As they burn through their hydrogen, they begin fusing heavier elements, pushing toward iron in their cores. Once iron forms, fusion stops. It's a dead end. Iron doesn't release energy when fused, but rather consumes it, leading to a violent collapse of the star's core. This collapse sets off a supernova explosion and a cataclysmic event so powerful it can outshine an entire galaxy, leaving behind the remnants of a star's legacy in the form of a black hole or neutron star. Supernovas stand as some of the most awe-inspiring events in the universe, serving as the epic forges where the elements essential for life are forged. These cataclysmic explosions scatter the heavier elements, those beyond iron, across the cosmos, enriching the very fabric of space with the building blocks for new worlds. When a star reaches the end of its life, it doesn't simply fade away. It erupts in a brilliant supernova, sending shockwaves of energy that reverberate through space, creating the necessary conditions for new stars, planets, and even life to emerge. But what happens after the dust settles? The remnants of a supernova can either condense into a neutron star, an incredibly dense object made almost entirely of neutrons, or collapse even further to form a black hole, a region of space where gravity is so intense that not even light can escape. These remnants, whether in the form of neutron stars or black holes, are more than just the remnants of an explosion. They are the very engines of the cosmos. Neutron stars, with their intense magnetic fields and rapid rotation, become cosmic lighthouses, emitting powerful beams of radiation, while black holes, shrouded in mystery, govern the dynamics of entire galaxies, regulating star formation and the evolution of galactic structures. In a broader sense, Stars themselves are the universe's ultimate creators, sculpting the elements that make up everything we know, from the carbon in our bodies to the iron in the core of Earth. Every atom that makes up our world, from the oxygen we breathe to the iron in our blood, can trace its origins back to the heart of a star or the violent blast of a supernova. This intricate connection between stars and life gives us a profound sense of being intimately tied to the cosmos. Supernovae don't just mark the end of a star's life, they are integral to the ongoing cycle of creation. These explosions are the key to spreading elements heavier than iron into the interstellar medium, elements necessary for the formation of planets and the development of life. The energy unleashed during a supernova also influences the surrounding gas and dust, sometimes igniting new stars or sweeping material away in other regions, further shaping the universe in an ongoing process of cosmic evolution. As we move from the realm of supernovae to their remnants, neutron stars stand out as incredible cosmic laboratories. Formed from the collapsed cores of massive stars, these objects are so dense that a single teaspoon of neutron star material would weigh about as much as Mount Everest. Despite their small size, typically only about 20 kilometers in diameter, neutron stars contain masses comparable to that of the Sun, packed into an almost unimaginable density. Their intense gravitational fields and magnetic forces produce phenomena like pulsars, which emit rhythmic bursts of radiation, offering us a glimpse into the extreme environments that exist far beyond Earth. And then there are black holes, perhaps the most enigmatic of all cosmic phenomena. Formed from the collapse of supermassive stars, black holes defy comprehension. At their core lies a singularity, a point where gravity is so intense that time and space themselves are distorted. The discovery of black holes, long predicted by Einstein's theory of general relativity, has opened an entirely new chapter in our understanding of the universe. Supermassive black holes, in particular, reside at the centers of galaxies, influencing the formation of stars and shaping the very structure of galaxies. Their immense gravitational pull and the energetic processes surrounding them, such as the accretion of matter, serve as the engines that drive the evolution of galaxies over cosmic timescales. Beyond their role in the synthesis of elements and the structure of the cosmos, supernovae, neutron stars, and black holes serve as natural laboratories for the study of physics under the most extreme conditions. These phenomena push the boundaries of what we know about gravity, density, and energy, providing us with insights that cannot be replicated on Earth. As scientists observe and model these celestial events, we gain new understanding about the nature of matter, space, and time itself, challenging and expanding the limits of human knowledge. But the story of the universe doesn't end with the explosive death of stars. As these stars give birth to new elements, they also set the stage for the formation of planetary systems. The birth of planets follows a similar process to that of stars, beginning with the collapse of molecular clouds of gas and dust. As pockets of this cloud collapse under their own gravity, a rotating disk of material forms around a new star. This disk, the cradle of planets, becomes the stage for the intricate dance of planet formation. Within these swirling clouds of gas and dust, particles collide and clump together, eventually forming the diverse worlds that orbit stars across the cosmos. It's in these planetary systems that the story of life as we know it unfolds, with stars and their planetary companions taking shape over billions of years. But over time, within the swirling disk of gas and dust that surrounds a young star, particles begin to collide, sticking together in a chaotic dance. Slowly, these clumps grow larger, eventually forming planetesimals, the building blocks of planets. Through a relentless process of accretion, these planetesimals continue to collide and merge, becoming increasingly massive and giving rise to protoplanets. The temperature gradient across the disk plays a key role in determining the nature of these growing worlds. In the hotter, inner regions, rocky planets like Earth and Mars take shape, while in the cooler outer reaches, ice forms and gas giants, along with icy worlds, emerge. However, the journey from a disk of debris to a vibrant planetary system is far from simple. Numerous factors influence the process, none more crucial than the properties of the central star itself. The star's mass, luminosity, and magnetic activity can alter the way planets form and even affect their eventual compositions. As the system evolves, interactions between these young planets can lead to dramatic changes. Planets may be ejected or collide, merging into larger bodies in a game of cosmic billiards. Yet not all planets are created equal, and when we consider the potential for life elsewhere, the concept of the habitable zone, or the Goldilocks zone, becomes pivotal. This is the narrow range of distances from a star where temperatures are just right, neither too hot nor too cold for liquid water to exist on a planet's surface. Liquid water, as we know, is vital for life. But a planet's position in the habitable zone is just one element of the complex equation of habitability. The presence of an atmosphere and a magnetic field is equally important. An atmosphere serves to regulate temperature, shielding the surface from harmful radiation while providing the essential ingredients for life. Meanwhile, a magnetic field acts as a guardian, protecting the atmosphere from the erosive forces of solar wind. Together, these factors work in harmony to create an environment where life could potentially thrive. The planet's composition, geological activity, and the presence of liquid water are also critical. Geological processes, such as plate tectonics, can regulate carbon levels and stabilize the climate over long periods, ensuring conditions remain favorable for life. In the ongoing search for exoplanets, planets orbiting stars beyond our solar system, a wide array of techniques is employed, each revealing new worlds in the vast cosmos. The goal is clear: to answer the age-old question that has captivated humanity for centuries: are we alone in the universe? The transit method is one of the most successful techniques, detecting the subtle dimming of a star's light as a planet passes in front of it. This approach has been incredibly fruitful, thanks to missions like NASA's Kepler Space Telescope, which monitored thousands of stars and discovered a treasure trove of exoplanets. Another method, known as radial velocity, measures the slight wobble of a star as it is tugged by the gravity of an orbiting planet, offering insights into the planet's mass and orbit. Direct imaging, though technically challenging, allows astronomers to capture actual images of exoplanets, blocking out the star's overwhelming light to study the planet's atmosphere. Another intriguing technique, gravitational microlensing, uses the gravitational field of a planet to magnify the light of a distant star, revealing the presence of an orbiting planet. Among the thousands of exoplanets discovered, several have captured the imagination of scientists and the public alike due to their unique characteristics or potential habitability. Kepler 22b, one of the first planets found in the habitable zone of its star, sparked excitement about the possibility of liquid water on its surface. Similarly, TRAPPIST-1e, part of a 7-planet system orbiting the dwarf star TRAPPIST-1, stands out for its potential to support water and life. Another fascinating world is Proxima Centauri b, located in the habitable zone of Proxima Centauri, the closest star to the Sun. Its discovery ignited interest in studying a potentially habitable planet located relatively close in cosmic terms. Meanwhile, HD 29458b, known as Osiris, is notable for being the first planet where an atmosphere was detected. This breakthrough allowed scientists to begin unraveling the composition of exoplanetary atmospheres, offering a glimpse into the diverse environments that could exist beyond our solar system. The search continues, pushing the boundaries of our knowledge and bringing us one step closer to understanding the vastness of the universe and the potential for life elsewhere. Each of these discoveries brings an invaluable glimpse into the incredible variety and complexity of planetary systems scattered across the galaxy. Not only do they reveal the endless possibilities for worlds beyond our own, but they also highlight the astonishing advancements in our ability to detect and study far-flung realms. With each breakthrough, we draw nearer to understanding the conditions that might support life elsewhere in the cosmos. But the search for exoplanets is far more than a journey of discovery. It pushes the very limits of our knowledge, constantly redefining our place in the universe. It's a reminder of the endless wonders that remain hidden, waiting to be uncovered in the dark expanse of space. When we turn our gaze to the most profound discoveries of modern cosmology, dark matter and dark energy, we see how they've reshaped our understanding of the universe itself. These invisible forces, elusive yet pervasive, are key to the way the universe has evolved and will continue to evolve. Dark matter is one such enigma, a mysterious substance that does not emit, absorb, or reflect light, making it entirely invisible to current telescopes. Despite its invisibility, its presence is undeniable, inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the cosmos. In the 1970s, Vera Rubin's groundbreaking work on galaxy rotation curves provided the first compelling evidence for dark matter. She discovered that stars at the edges of galaxies were moving far faster than they should, based on the visible matter alone. This discrepancy suggested that some unseen mass was affecting the galaxy's rotation, a discovery that would fundamentally alter the course of cosmology. Yet the mystery of dark matter doesn't end there. Gravitational lensing, an effect where the gravity of a massive object bends light from a more distant source, provides further evidence. The sheer amount of light bending observed implies a hidden mass far beyond what we can observe through conventional means, reinforcing the idea that dark matter constitutes a significant part of the universe's mass. And when we study the cosmic microwave background radiation, the relic glow from the Big Bang, the early universe's snapshot matches predictions only dark matter is considered, adding weight to its existence. As we contemplate the vast unknowns, dark energy presents itself as another cosmic puzzle. Unlike dark matter, which pulls matter together through gravity, dark energy drives the universe's accelerated expansion. The discovery of dark energy traces back to the late 1990s, when astronomers studying Type 1a supernova, known as standard candles for measuring cosmic distances, found that these supernovae were dimmer than expected. This unexpected faintness pointed to a fundamental shift in the universe's expansion, which was now accelerating, not decelerating. The culprit? Dark energy, which now makes up nearly 68% of the universe's total energy content. This revelation raises profound questions about the future of the universe. If dark energy continues to dominate, the universe might stretch into eternity, cooling and darkening as it expands into an ever more desolate state. Alternatively, if the nature of dark energy shifts, it could lead to wildly different outcomes, such as the universe's eventual collapse or an even faster, more chaotic expansion. Together, dark matter and dark energy form the cornerstone of the lambda cold dark matter model, our current framework for understanding the universe's evolution, from the fiery moments of the Big Bang to the vastness we see today. And still, the cosmos continues to surprise us. As we probe deeper into the heart of space, we encounter phenomena such as quasars, pulsars, and gamma-ray bursts, each one offering a rare and thrilling glimpse into the extremes of the universe's processes. Quasars, for example, are the fiercely radiant cores of distant galaxies, fueled by supermassive black holes. As matter falls into these black holes, it heats up, emitting immense amounts of energy across the spectrum: visible light, X-rays, and ultraviolet radiation. These quasar beacons shine as some of the brightest objects in the universe, their energy outshining entire galaxies. And though they are compact enough to fit within our own solar system, their brightness is a window into the past, shedding light on the formation of galaxies and the growth of supermassive black holes. Pulsars, in contrast, are the remnants of massive stars that exploded in supernovae, collapsing into neutron stars that are mind-bogglingly dense. These stars, no more than 20 kilometers across, contain masses comparable to the sun's, packing a staggering amount of material into a tiny space. Pulsars are not only strange and beautiful, but serve as cosmic clocks, helping scientists measure time and space with incredible precision. And these are just a few of the phenomena that paint a picture of a universe filled with extremes, a universe that continues to unfold its mysteries as we venture further into the unknown. Pulsars, those mysterious cosmic entities, emit beams of electromagnetic radiation from their magnetic poles. As they rotate, these beams sweep across the vastness of space, much like the focus beams of a lighthouse guiding the way. When Earth happens to intersect one of these beams, we detect pulses of radiation, hence the name pulsar. These celestial objects are not just sources of light, they are incredibly precise cosmic clocks. For astronomers, pulsars offer an extraordinary opportunity to explore the fabric of space itself and test theories of gravity with remarkable accuracy. Then there are the gamma-ray bursts, or GRBs, which stand as the universe's most energetic explosions. These fleeting events can briefly outshine entire galaxies, unleashing bursts of gamma rays that can last anywhere from a few milliseconds to several minutes. GRBs are thought to originate from two main cosmic phenomena: the collapse of massive stars into black holes, triggering supernova, or the catastrophic collision of neutron stars. Each burst offers a window into the processes behind these cataclysmic events and serves as a beacon to study the early universe. These bursts illuminate the rate of star formation and may even offer clues about the origins of heavy elements, key ingredients in the formation of planets and life as we know it. In the grand expanse of space, magnetic fields weave their influence across galaxies, stars, and interstellar mediums. These cosmic magnetic fields play an essential role in shaping the behavior of the universe, from guiding cosmic rays to influencing the formation of galaxies themselves. Generated by the motion of conductive fluids within stars and planets, a process known as the dynamo effect, or leftover from the early universe, these fields manifest in the movement of charged particles and the polarization of light emitted by distant stars. By studying these fields, astronomers can unravel the mysteries of galaxy formation, interstellar gas dynamics, and the behavior of astrophysical jets. Understanding these fields is not just about the forces they exert, but about the hidden structures they reveal within the vast cosmic landscape. The search for life beyond Earth continues to capture humanity's imagination and scientific curiosity. In this quest, scientists have identified a few essential conditions for life as we understand it to thrive: liquid water, a source of energy, and a suitable chemical environment. Water, as a solvent, facilitates the biochemical reactions needed for life. Energy fuels metabolic processes, and the right chemical elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are the building blocks of living organisms. The search for biosignatures, indicators of life, on exoplanets and within our solar system is pushing the boundaries of exploration. To detect life on distant exoplanets, scientists employ a variety of methods. One of the most promising techniques is the transit method, where a planet is observed as it passes in front of its host star. This allows scientists to study the planet's atmosphere, examining the starlight that filters through and identifying chemical signatures that could suggest biological activity. The detection of gases like oxygen, methane, or nitrous oxide, especially in combinations that are unlikely to occur through non-biological processes, may hint at the presence of life. Another innovative method is direct imaging, where light from the planets themselves is captured. While this is a significant challenge due to the faintness of the planets compared to their stars, advancements in technology are making this increasingly feasible. Direct imaging allows for the analysis of chemical compositions, thermal structures, and even surface features, opening a new frontier in the search for life. Closer to home, missions to Mars, including the rovers that traverse its surface, search for evidence of past or present microbial life. By analyzing rock and soil samples, these rovers seek signs of organic compounds, minerals related to water, and isotopic signatures that might indicate biological processes once occurred, or perhaps still do. Moons like Europa and Enceladus, orbiting Jupiter and Saturn, also hold promise in the search for life. Beneath their icy surfaces lie subsurface oceans, and upcoming missions aim to probe these waters for signs of life. Whether by sampling water plumes ejected into space or sending landers and ice-penetrating probes beneath the frozen crusts, these efforts bring us closer to answering one of the most profound questions of all: are we alone in the universe? And so the search for life beyond Earth extends to Venus. The discovery of phosphine gas in its atmosphere has sparked intense interest, even though the planet's harsh surface conditions would seem to make life impossible. While the presence of phosphine could be explained by non-biological processes, it highlights the wide range of environments where scientists are now exploring the potential for life beyond our planet. Human space exploration, which seeks to unravel the secrets of the cosmos while securing the long-term survival of humanity, faces an array of formidable challenges. These endeavors, ambitious in scope, are not without their hurdles. From the technical and physiological obstacles of long-duration travel to the logistical and ethical complexities of colonization, the boundaries of our technology and resilience are constantly tested. One of the most pressing concerns in extended space travel is safeguarding the health and well-being of astronauts. In space, extended missions expose crews to a host of risks: the detrimental effects of microgravity on muscle and bone density, heightened radiation exposure beyond Earth's protective magnetosphere, and the psychological toll of isolation and confinement. To tackle these issues, innovative solutions are needed. These include advancements in radiation shielding, specialized exercise regimes to counteract muscle and bone degradation, and comprehensive mental health support strategies. The development of life support systems that can sustain human life for long periods is another critical challenge. These systems must ensure astronauts have access to air, water, and food, with a focus on recycling as much as possible to reduce the need for resupply missions. Progress in closed-loop life support technology, which converts waste products back into reusable resources, is essential for both long-duration missions and the viability of space habitats. Equally important are the technical challenges of propulsion and energy. Current spacecraft propulsion technologies impose limitations on travel speed, lengthening mission durations, and increasing the exposure of astronauts to the dangers of space. Advances in propulsion systems, such as nuclear thermal or electric propulsion, could revolutionize space travel, cutting down travel time to distant destinations like Mars and making these missions more practical. In addition, reliable energy sources are essential. Solar power, nuclear reactors, and the concept of in situ resource utilization, where astronauts extract materials from planets and moons, are all being investigated as potential solutions. As humanity's presence in space grows, the ethical and logistical aspects of colonization and exploration become ever more pressing. Who will have the right to explore or settle on new planets? How can we protect the pristine environments of other worlds? The development of legal and ethical frameworks for space exploration and the sustainable use of extraterrestrial resources is vital for the future of our spacefaring endeavors. The goals of human space exploration are as varied as they are ambitious. They range from conducting groundbreaking scientific research to uncover the mysteries of the universe, searching for extraterrestrial life, testing new technologies, and ultimately establishing colonies on other planets to ensure the survival of the human race. Mars, with its Earth-like characteristics, remains the focal point for colonization efforts, but the Moon is seen as an essential first step for deeper space exploration. Then, there are the mysterious phenomena that captivate the imagination of scientists and the public alike. Fast radio bursts, FRBs, are among the most enigmatic of these cosmic puzzles. These brief yet intense bursts of radio waves, lasting only milliseconds, release as much energy as the Sun does in days or even weeks. Discovered in 2007, FRBs have left astronomers scrambling for explanations, driving a surge of research into their origins and potential significance. Though their flashes are fleeting, FRBs have been detected from billions of light years away, their brilliance defying the vast distances between us and their source. Some FRBs emit only a single burst, while others repeat in regular intervals, leading scientists to propose various potential origins. Some suggest highly magnetized neutron stars, known as magnetars, are responsible for the phenomenon, their explosive activity releasing vast amounts of energy. Others have entertained more speculative ideas, including the possibility that these bursts might be linked to black holes or, though highly controversial, even signals from advanced extraterrestrial civilizations. The study of fast radio bursts is not just about solving the mystery of these flashes. In fact, these bursts could serve as invaluable tools for understanding the universe itself, acting as cosmic messengers that might unlock deeper insights into the nature of space and time. Due to their journey through the vast expanses of the universe, fast radio bursts, FRBs, interact with the intergalactic medium, offering a rare and valuable opportunity for scientists to explore the unseen matter scattered throughout the cosmos. As these bursts travel across light years of space, they encounter electrons and magnetic fields that alter their properties. This interaction provides critical clues about the distribution of matter across the universe, including the mysterious and elusive dark matter that has long perplexed astronomers. Moreover, FRB's distinct localization to specific galaxies opens up new and promising pathways for cosmological studies. By measuring the dispersion and delay of the signals caused by their interaction with cosmic matter, astronomers can gain insight into the universe's large-scale structure. This data also enables scientists to test fundamental theories of gravity and relativity over vast cosmic distances, refining our understanding of the laws that govern the universe. The ongoing detection and study of FRBs, driven by advancements in telescope technology and global collaboration among observatories, hold immense promise. Each new discovery brings us one step closer to unlocking not just the nature of FRBs, but also the fundamental properties of the universe itself. From the distribution of dark matter to the extreme environments around compact objects like neutron stars and black holes, these cosmic enigmas offer a wealth of knowledge that could revolutionize our understanding of the universe. Now let's shift our focus to another cosmic mystery: rogue planets. These enigmatic wanderers of the universe defy our traditional understanding of planetary systems. Rogue planets do not orbit a star, but instead drift freely through space, untethered and solitary. These mysterious objects challenge everything we thought we knew about planetary formation and the diversity of the cosmos. The origins of rogue planets are as intriguing as they are diverse. Some may have once orbited a star, but were cast out into the void through gravitational interactions, either with other planets in their system or as a result of a passing star's disruptive force. Others might have formed independently in vast molecular clouds, much like stars, but failed to accumulate enough mass to ignite the nuclear fusion necessary for stellar birth. These processes shed light on the chaotic and delicate nature of young planetary systems, where gravitational forces can disrupt orbits and eject planets into the unknown. Rogue planets are not only captivating because of their lonely voyages across the galaxy, but also because of the profound implications they carry for our understanding of planetary systems. Their discovery suggests that planetary formation is far more dynamic and diverse than previously imagined. In fact, some researchers theorize that rogue planets could outnumber stars in our galaxy, suggesting a vast, unseen population of worlds drifting in the darkness of space, far beyond our reach. The study of rogue planets, however, presents significant challenges. Without the warmth and light of a nearby star, they are incredibly difficult to detect. Yet, advancements in techniques like gravitational microlensing, where a rogue planet passes in front of a distant star and magnifies its light, have provided some of the first evidence of these elusive worlds. As technology continues to advance, future observations may yield valuable insights into the size, composition, and surface conditions of these mysterious planets, revealing new possibilities for the kinds of environments that may exist beyond the traditional habitable zones of stars. One of the most fascinating questions surrounding rogue planets is whether they could harbor life. While the lack of a host star might seem to rule out the possibility of life-supporting conditions, theories propose that rogue planets could maintain thick atmospheres or internal heat sources, such as residual heat from their formation or radioactive decay. These internal energy sources might offer a stable environment where life could thrive, challenging our conventional notions of habitability and expanding the search for life beyond the confines of star systems. Delving deeper into the unexplained phenomena of the cosmos, the WOW signal stands as one of the most captivating and enduring mysteries in the search for extraterrestrial intelligence. Detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University, the WOW signal was a sudden and intense radio burst lasting 72 seconds, originating from the direction of the constellation Sagittarius. This enigmatic signal, unlike any other radio signal detected before or since, continues to fuel speculation and intrigue about the possibility of intelligent life beyond Earth. The signal's intensity and the unusual characteristics it exhibited were so remarkable that, upon reviewing the data, astronomer Jerry R. Eman could not contain his astonishment. He circled the alphanumeric sequence 6EQUJ5, a direct representation of the signal's intensity, and scrawled "Wow" in the margin, forever linking his reaction to the signal's mystique. And thus, the WOW signal was born, a name that would carry the weight of decades of scientific speculation and intrigue. The origins of this enigmatic signal have remained elusive, sparking decades of investigation. Its narrowband frequency, eerily close to the hydrogen line, 120 megahertz, was something one might expect from an intentional transmission. Hydrogen, the most abundant element in the universe, makes this frequency a logical candidate for interstellar communication. However, despite extensive efforts to detect the signal again, it has never reappeared, leaving astronomers and scientists to ponder its mysterious source. Theories abound, ranging from interstellar scintillation and the interference of a passing comet to the possibility of a brief burst of natural background noise. Yet none of these explanations have definitively solved the riddle, leaving room for one tantalizing theory, that the signal could have been a transmission from an extraterrestrial civilization. The implications of the WOW signal reach far beyond the boundaries of its mysterious origin. It has become a cornerstone in the search for extraterrestrial intelligence, SETI, not only fueling the hope of discovering intelligent life beyond Earth, but also highlighting the immense challenges that lie in the detection and interpretation of such signals. Its discovery has propelled advancements in observational technology, inspiring the development of more sensitive detection methods and refined protocols for verifying extraterrestrial transmissions. More than just a scientific anomaly, the WOW signal has ignited the public's imagination, serving as a poignant reminder of humanity's place in the vast cosmos and of the possibility that we might not be alone. As we consider the future of the universe, we are confronted with questions that challenge the very nature of existence itself. Cutting-edge theories, such as string theory, the multiverse, and the speculative notions of wormholes and time travel, push the boundaries of our understanding. These ideas do not just expand our knowledge of the universe, but also invite us to explore profound questions about the very fabric of reality. Among the most widely discussed potential fates of the universe is the continued acceleration of its expansion. This scenario, known as the Big Freeze or heat death, envisions a universe that stretches endlessly, with stars burning out and galaxies drifting apart until the cosmos becomes a cold, dark, and lifeless expanse. This prediction is supported by the discovery of dark energy, a mysterious force that appears to be driving the universe's accelerated expansion. But there's another possibility, the Big Crunch. In this scenario, the expansion of the universe reverses, causing all matter and energy to collapse back into a singularity, possibly triggering another Big Bang. However, current evidence suggests that the universe's expansion is speeding up, making this possibility less likely with each passing year. Theoretical frameworks like string theory offer a deeper understanding of the universe's structure. String theory proposes that the fundamental building blocks of the universe are not particles, but rather one-dimensional strings that vibrate at different frequencies. This theory also lays the foundation for the concept of the multiverse, the idea that our universe may be just one of many, each with its own unique physical laws and constants. Such a notion challenges the idea of a singular, unique universe, and opens the door to the possibility of universes where the very fabric of reality might be vastly different from our own. Then there are wormholes, hypothetical passages through the fabric of spacetime that could allow for shortcuts between distant points in the universe or even between entirely different universes. Though purely speculative and riddled with theoretical obstacles, wormholes captivate the imagination. They hold the tantalizing possibility of enabling interstellar travel or even interuniversal exploration, raising the prospect of bridging the vast distances that separate the stars. And what about time travel? While traveling to the future, thanks to the relativistic effects of time dilation, is theoretically possible, the idea of traveling to the past presents profound paradoxes that challenge the very foundations of physics. Yet the very exploration of time travel forces us to confront the nature of causality, the arrow of time, and the structure of spacetime itself, questions that could one day reveal untold truths about the universe. And as we venture into the realm of the unknown, we are constantly confronted with the limits of our understanding and the vast expanse of what lies beyond our reach. The questions surrounding the fate of the universe, the very existence of a multiverse, and the tantalizing possibilities of wormholes and time travel not only stretch the boundaries of what we know, but challenge the fundamental fabric of existence itself. These concepts compel us to rethink everything we thought we understood about the cosmos. As we peer further into the mysteries of space, we not only extend the frontiers of science and philosophy, but we are also on a perpetual quest to unravel the nature of our place in this vast universe. When it comes to the search for alien life, humanity's fascination with the possibility of extraterrestrial intelligence has long been a subject of intrigue. For decades, scientists and the general public alike have wondered whether we are truly alone in the cosmos. This search for life beyond Earth has led to the development of multiple scientific frameworks, one of the most significant being the Drake equation. Proposed by astronomer Frank Drake in 1961, the equation provides a probabilistic method for estimating the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Through a synthesis of key variables, such as the rate of star formation, the number of stars with planets, and the likelihood that life will evolve on those planets, Drake's equation attempts to quantify the potential for intelligent life to exist elsewhere in the universe. However, despite its elegance, the Drake equation also highlights the vast uncertainty that persists in our understanding of life's origins and the evolution of advanced civilizations. Many of the factors in the equation remain unknown, and the true values of these variables are subject to much speculation. This uncertainty stems from our limited understanding of the processes that give rise to life, as well as the enormous complexity and size of the Milky Way. As a result, estimates of the number of civilizations capable of communication range from optimistic to near zero, with little consensus within the scientific community. Yet, the equation remains a cornerstone of discussions on the subject of extraterrestrial life, directing research and sparking debates that extend into the realms of astrobiology and the search for extraterrestrial intelligence. SETI, which is dedicated to detecting signs of intelligent life from beyond our world, is deeply influenced by the framework laid out in the Drake equation. Using advanced technology, SETI researchers monitor radio and optical signals that may emanate from extraterrestrial technologies. While no definitive evidence of alien intelligence has been found, the continued efforts of SETI reinforce our enduring curiosity and commitment to exploring the possibility that we are not alone in the universe. Yet, even as we continue to search for signs of extraterrestrial life, we encounter a paradox. The Fermi paradox. Named after the renowned physicist Enrico Fermi, this paradox presents a striking contradiction. If the likelihood of extraterrestrial civilizations is so high, why then do we find ourselves in a cosmic silence? With billions of stars scattered across our galaxy, each potentially harboring planets that could sustain life, and given the immense age of the universe, there should be ample time for intelligent life to arise and send signals across the cosmos. However, despite decades of searching, we have found nothing but a vast emptiness. This silence raises profound questions about life in the universe. Several hypotheses have been put forward to explain the Fermi paradox. One possibility is that while life may be abundant, the emergence of intelligent civilizations capable of interstellar communication is extraordinarily rare. Another hypothesis, known as the Great Filter, suggests that there is a highly improbable step in the evolutionary process that must be overcome for life to develop intelligence and technological capability. Perhaps humanity has already passed this filter, or perhaps it lies ahead, threatening the very survival of our species. Other theories propose that civilizations may simply be short-lived, either destroying themselves through technological means or evolving beyond the need for detectable signals. Some even speculate that advanced extraterrestrial civilizations may intentionally avoid us, following a zoo hypothesis where they observe us from afar, refraining from contact to allow us to develop naturally. And as we look beyond the search for alien life, we also confront the mysteries of space itself. The cosmos is full of phenomena that defy our understanding, from black holes to dark matter. One of the most perplexing cosmic anomalies is the Great Attractor, a massive, invisible region in space that seems to possess an immense gravitational pull. This mysterious area, located approximately 220 million light-years away in the direction of the Hydra and Centaurus constellations, influences the movement of galaxies across vast distances. Astronomers have discovered that galaxies, including our own Milky Way, are being drawn toward the Great Attractor at staggering speeds, potentially shedding light on some of the most fundamental forces that govern the universe. Yet, despite its immense power and influence, we still know remarkably little about the true nature of this gravitational anomaly, and its origins remain one of the great unsolved mysteries of modern astronomy. In confronting these enigmas, we are reminded of the vastness of the universe and the ever-expanding frontier of human knowledge. Every discovery, every new theory only deepens the mystery. And as we continue to explore, one thing becomes abundantly clear. The more we learn, the more we realize how much we have yet to understand. The study of the Great Attractor presents a unique challenge due to its location in the zone of avoidance, an area of the sky shrouded in the dense dust and gas of the Milky Way's galactic plane. This cosmic obscurity makes direct observation incredibly difficult. Yet, despite these hurdles, breakthroughs in X-ray and radio astronomy have allowed scientists to peer through the interstellar fog, slowly unlocking the secrets of this enigmatic force. The Great Attractor, as it turns out, is not a singular, massive entity, but a collection of galaxy clusters. This vast concentration is part of something even larger, the Laniakea supercluster, a sprawling cosmic structure that encompasses not just our Milky Way, but around 100,000 other galaxies. The gravitational pull of the Great Attractor and its influence on the motion of galaxies provide a striking example of the interconnectedness of cosmic structures. This immense, unseen force pushes us to reconsider the scale and complexity of the universe, a reminder that forces far beyond our understanding continue to shape the cosmos in ways we're only beginning to comprehend. And just as the Great Attractor reveals the unseen forces at work in the cosmos, the orbits of unusual comets present their own mysteries, enigmas that continue to intrigue scientists and astronomers alike. These so-called dirty snowballs, made of ice, rock, and organic compounds, carry us into the far reaches of our solar system, offering glimpses into the hidden dynamics of space. Some comets follow wildly eccentric orbits, approaching the sun to develop brilliant tails before retreating back into the void, or even being ejected from the solar system entirely. These unpredictable paths raise fascinating questions about the hidden forces at play in the outer solar system. One possibility is the gravitational influence of the Oort cloud and the Kuiper belt, vast, icy regions that extend far beyond Neptune's orbit. The Oort cloud, a spherical shell of icy bodies, is thought to house billions of comets. Occasionally, the gravitational tugs of passing stars or the Milky Way's galactic tide can disturb these comets, sending them on dramatic journeys toward the sun. But even more intriguing is the idea of a large, as yet undiscovered object lurking in the outer solar system, one that might be influencing the orbits of these distant objects. Known as Planet 9, this hypothetical planet could account for some of the most bizarre comet trajectories, nudging them into pathways that defy conventional explanations. By studying these erratic comet orbits, scientists gain critical insights into the outer regions of our solar system, shedding light on its hidden mass distribution and offering clues about possible interactions with interstellar objects. As our observational tools and computational models improve, so too will our understanding of these celestial wanderers, offering answers to long-standing questions and raising new mysteries about the cosmic dance that governs our solar system. Then there are Titan and Enceladus, Saturn's moons that have captured the imagination of scientists with their extraordinary features. Titan, Saturn's largest moon and the second largest in the entire solar system, is enshrouded in a thick, nitrogen-rich atmosphere, rich in organic compounds. Some of these molecules are essential building blocks of life, making Titan a fascinating subject in the search for extraterrestrial life. Beneath its hazy veil, Titan's surface is dominated by rivers, lakes, and seas, but not of water. Instead, these liquid bodies are made of methane and ethane, hydrocarbons that present an environment entirely different from Earth, yet possibly capable of supporting life forms adapted to such cold, alien conditions. Titan's weather system also mirrors Earth's in striking ways, but with methane and ethane instead of water. A cycle of clouds, rain, and liquid lakes on its surface offers an astonishing parallel to our planet's hydrological processes, though in a context utterly foreign to us. The similarities and the differences present intriguing possibilities for the nature of life in such an environment. Enceladus, though much smaller, is no less captivating. This moon is famous for its geysers, plumes of water vapor and ice particles erupting from cracks in its icy surface. These geysers offer tantalizing evidence that beneath Enceladus's frozen exterior, there may be a subsurface ocean, a potential cradle for life, hidden away from the harsh surface conditions. Together, Titan and Enceladus challenge everything we thought we knew about the potential for life beyond Earth, offering up clues about the diverse and complex environments that may exist in our own solar system and beyond. The more we learn, the more we realize just how much there is still to discover. These geysers erupt from beneath the icy shell of Enceladus, hinting at something much deeper, a hidden subsurface ocean. This remarkable discovery stirs the imagination, raising the tantalizing possibility that beneath the moon's frozen exterior, there could be a thriving environment capable of supporting life. The geysers, which spew a mix of water vapor and icy particles, have captivated scientists and astronomers alike. This ejected material, much of it contributing to the formation of one of Saturn's iconic rings, has been directly sampled by spacecraft. What these samples reveal is nothing short of extraordinary. Complex organic compounds, salts, and even silica particles. These organic compounds are significant because they suggest that the ocean beneath Enceladus's icy crust is not just a simple reservoir of liquid water. It also indicates a profound interaction with the moon's rocky mantle, where hydrothermal processes might be occurring. Such processes, akin to those that sustain life in the darkest depths of Earth's oceans, could be providing the essential energy needed for life to take hold. In the shadow of this discovery, Titan, Saturn's largest moon, presents an entirely different, yet equally fascinating story. Titan's thick, nitrogen-rich atmosphere and cold hydrocarbon lakes create a radically different environment from anything we recognize as habitable. Nonetheless, Titan challenges our very definition of habitability. While its cold and distant landscape may seem inhospitable, it sparks a crucial question. Could life in some form exist in a world built on methane rather than water? Together, the phenomena observed on both Titan and Enceladus expand the boundaries of our understanding of what constitutes a potentially habitable environment. Titan's frigid, hydrocarbon-based system pushes the limits of imagination while Enceladus offers a more familiar and yet equally mysterious water-based habitat beneath layers of ice. These moons are living proof of the many varied ways that life might not only exist but thrive in environments vastly different from Earth's. As missions continue to probe the secrets of these moons and others in our solar system, we edge ever closer to understanding the complexity of these worlds that could one day tell us something crucial about the potential for life beyond our planet. But these discoveries don't just challenge our ideas of extraterrestrial life. They also push the boundaries of physics itself, offering glimpses into the nature of space and time. At the heart of this exploration lies the concept of space-time, a revolutionary idea that reshaped our understanding of the cosmos. In the early 20th century, Albert Einstein's theory of general relativity showed us that the universe is not just a stage where events unfold. Instead, space-time itself is a dynamic and flexible fabric shaped by the presence of mass and energy. Far from being a passive backdrop, space-time interacts with the objects within it, dictating their movement and influencing the flow of time itself. Think of space-time as a vast four-dimensional continuum. The three dimensions of space, length, width, and height, are woven together with time into a single inseparable entity. The presence of a massive object like the Earth or the Sun warps this fabric, creating what we perceive as gravity. When Earth orbits the Sun, it is not because the Sun is pulling on it directly. Rather, it's because the Sun's immense mass has curved space-time, causing Earth's path to bend into an elliptical orbit. This insight into space-time has profound implications that reach far beyond the simple motion of planets. The way light behaves, the passage of time, and even the structure of the universe itself are all shaped by the curvature of space-time. Light, though massless, is affected by this curvature. This is evident in the phenomenon of gravitational lensing, where light from distant stars is bent by the gravitational influence of massive objects, like galaxy clusters, distorting our view of the cosmos. Time, too, is a casualty of spacetime's warping. In stronger gravitational fields, time slows down, an effect confirmed by precise experiments. This phenomenon, known as gravitational time dilation, isn't just a theoretical curiosity. It has practical applications. For example, adjustments must be made to synchronize the clocks on GPS satellites in orbit with those on Earth, due to the differences in gravitational pull and, consequently, the passage of time. As we delve deeper into the mysteries of spacetime, we uncover even more profound phenomena. The most extreme distortions occur in black holes, regions where spacetime itself is warped to such an extent that nothing, not even light, can escape. Black holes challenge our understanding of the universe's laws, forcing us to confront the limits of physics as we know it. Meanwhile, the expansion of the universe suggests that spacetime itself is stretching, carrying galaxies farther apart with each passing moment. This stretching of spacetime explains the observed redshift of distant galaxies as their light becomes stretched into longer wavelengths, a sign that the universe itself is growing. One of the most intriguing aspects of modern cosmology is the idea of a finite yet unbounded universe. This concept offers a way to reconcile the vastness of the cosmos with the possibility of it having a limited volume. How can something be both finite and unbounded? The answer lies in the geometry of spacetime. Just as the surface of the Earth is finite, there is a limited area, but has no edges, the universe can be finite in size but still have no edge where it ends. This mind-bending idea offers a glimpse into the true nature of the universe, showing us that reality is far more complex and far more wondrous than we ever imagined. Extending this analogy into the vast three-dimensional expanse of the universe, we find that the cosmos itself may exhibit a curvature, one that loops back onto itself in a higher dimension, thereby creating what we call a closed geometry. Picture this. If we had the capability to travel through the universe in a straight line, we would eventually return to the place where we began, without ever encountering a traditional edge or boundary. This curious idea emerges from the principles outlined in Einstein's theory of general relativity, which introduces a mind-bending concept, different potential shapes for the universe, each contingent on its density and how it continues to expand. In a closed universe, a universe that is finite yet unbounded, the density would be so high that it would halt the universe's expansion, eventually reversing its trajectory and causing the universe to collapse back in on itself, leading to what is known as a big crunch. It's an idea that seems almost outlandish, but it's an intriguing scenario nonetheless. Current evidence, though, paints a different picture. Observations, such as those of the cosmic microwave background radiation and the precise measurements of the universe's ongoing expansion, suggest that the universe on its grandest scales appears flat, perhaps even infinite in size. Nevertheless, the notion of a finite, unbounded universe continues to captivate the imagination, offering fertile ground for theoretical physicists to explore. But the true mind-expanding potential of the universe doesn't stop here. Imagine, if you will, a reality where the universe extends beyond the three spatial dimensions and one time dimension that we experience every day. This opens the door to entire realms of possibilities, stretching our understanding to its very limits. This concept, central to some of the most advanced theories in physics, including string theory and M theory, proposes that there are more dimensions than we can directly observe. In the world of string theory, particles are not mere point-like entities as once imagined, but rather one-dimensional strings vibrating at different frequencies. These vibrations govern the properties of particles, such as mass and charge. To ensure that string theory remains consistent, it requires additional spatial dimensions, specifically 10 total dimensions, 9 spatial dimensions plus 1 time dimension. These extra dimensions are believed to be curled up so tightly at scales far smaller than anything we can currently detect that they remain hidden from view. Yet, these hidden dimensions could unlock explanations for some of the most puzzling phenomena in physics, such as why gravity appears so much weaker compared to the other fundamental forces. If gravity could leak into these extra dimensions, it might explain why its influence is far less noticeable than, say, electromagnetism or the strong nuclear force. Moreover, the concept of higher dimensions suggests an even more extraordinary structure to the universe. The idea of parallel universes or multiple brains, multidimensional objects floating in a higher dimensional space, becomes a tantalizing possibility. In this scenario, our observable universe could be confined to one of these brains, while interactions between different brains in the higher dimensional realm could potentially give rise to profound events in our own universe, such as the Big Bang itself. The pursuit of understanding higher dimensions also ties into one of the most ambitious goals in modern physics, the quest for a theory of everything. This theoretical framework aims to seamlessly unify the forces that govern the universe, from the vastness of general relativity, which explains the workings of the cosmos on a large scale, to quantum mechanics, which governs the incredibly small particles that make up the fabric of matter. And in this search for unity, higher dimensions could very well provide the missing link, bridging the gap between the macroscopic and microscopic worlds. But while the universe operates on mind-bending scales and with mind-bending possibilities, there is one force in our immediate neighborhood that demands our attention: the sun. At the heart of our solar system, the sun is an immense fiery ball of plasma, a furnace that produces energy through nuclear fusion. Deep within its core, hydrogen atoms are compressed and heated to such extremes that they fuse into helium, releasing enormous amounts of energy in the process. This nuclear fusion is the source of the sun's intense light and heat, powers life on Earth, and drives the vast dynamics of the entire solar system. Without this constant energy output, life, as we know it, would be impossible. But what fuels the sun's brilliance and warmth? At its core, an extraordinary process unfolds, one that has been powering the sun for billions of years. Here, at temperatures exceeding 15 million degrees Celsius or 27 million degrees Fahrenheit, hydrogen atoms are squeezed under immense pressure, overcoming their natural resistance. This extreme environment ignites the proton-proton chain reaction, where hydrogen nuclei protons merge to form helium-4, releasing vast amounts of energy. This fusion process converts small amounts of mass into energy in accordance with Einstein's iconic equation E equals mc squared. The energy, initially released as gamma rays, embarks on a journey to the sun's surface, a journey that takes thousands of years to complete. When this energy finally reaches the sun's surface, or photosphere, it emerges as sunlight, having transformed into visible light and other forms of electromagnetic radiation. This process is astonishingly efficient, with millions of tons of hydrogen turning into helium every second. Yet, it is also slow enough that the sun has been shining for about 4.6 billion years, and will continue to shine for roughly 5 billion more. Its stability and energy output are vital to life on Earth, offering the warmth and light that sustain countless life forms. However, the sun's activity isn't just about providing light and heat. It also gives rise to solar phenomena that can affect Earth in profound ways. From solar flares to coronal mass ejections, CMEs, and solar wind, these phenomena influence everything from Earth's climate to our modern technology. Solar flares, for example, are sudden bursts of radiation from the sun, caused by the release of magnetic energy linked to sunspots. The light from a flare reaches Earth in just 8 minutes, but the high-energy particles it releases can take hours or even days to arrive. When they do, they can disrupt radio communications, GPS signals, and even power grids by ionizing the ionosphere, the Earth's upper atmosphere, and interfering with the transmission of radio waves. Then there are the coronal mass ejections, or CMEs, massive eruptions of solar wind and magnetic fields that rise above the sun's corona. CMEs can launch billions of tons of material into space, carrying a magnetic field that is stronger than the background solar wind's interplanetary magnetic field. When these energetic bursts collide with Earth's magnetosphere, they can spark geomagnetic storms that disrupt satellite operations, power grids, and navigation systems. But CMEs also create one of the most stunning natural phenomena on Earth, auroras, or the northern and southern lights, which light up the skies near Earth's polar regions. Solar wind, a continuous stream of charged particles released from the sun's corona, also has a profound effect on Earth. This stream constantly interacts with Earth's magnetic field, compressing it on the sun-facing side and stretching it on the opposite side, creating a magnetic tail. When this charged wind collides with particles trapped in the magnetosphere, it can energize them, causing them to move into Earth's upper atmosphere and create dazzling auroras. The intensity of solar wind varies, but it remains a steady presence, influencing everything from geomagnetic storms to the appearance of auroras. The Sun also follows an 11-year cycle known as the solar cycle, which sees the frequency of sunspots, solar flares, and CMEs fluctuate. This rhythm of solar activity can affect Earth's climate and space weather. During periods of maximum solar activity, the Sun emits increased ultraviolet radiation, which boosts ozone production in Earth's stratosphere. This, in turn, can influence atmospheric circulation patterns, affecting regional weather and climate. Even more remarkably, there is evidence suggesting that prolonged periods of low solar activity, such as the Maunder minimum in the 17th century, may be linked to cooler global temperatures, an intriguing connection between the Sun's behavior and Earth's climate. In short, the Sun is not just a passive source of light and heat. It is a dynamic, ever-changing force that shapes life on Earth in ways both subtle and dramatic. Moreover, the increasing dependence on technology is rapidly transforming our society, rendering it increasingly vulnerable to the unpredictable forces of solar storms. These storms, with their potential to disrupt communication and navigation systems, underscore the critical need for continuous monitoring of solar activity. In a world where technology underpins nearly every aspect of our daily lives, understanding and preparing for such cosmic phenomena is no longer a luxury. It is a necessity. Speculating about the existence of advanced civilizations beyond our own opens a fascinating gateway into both scientific exploration and philosophical inquiry. These civilizations, if they exist, would likely surpass us in ways we can scarcely imagine. With mastery over technology and societal structures far more sophisticated than our own, such civilizations could hold the key to understanding the future of intelligent life in the universe. To explore their potential characteristics, we turn to frameworks like the Kardashev scale, a classification system that gauges a civilization's energy consumption and technological prowess. A Type 1 civilization, according to the Kardashev scale, harnesses all the energy available on its home planet. This level of advancement implies a complete mastery of natural resources, including solar energy, geothermal energy, and other sustainable power sources. Such a society would have likely solved many of the critical challenges we face today, from climate change to energy scarcity. These civilizations would not only excel in resource management, but also exhibit remarkable advancements in sustainability. They might be capable of seamlessly recycling waste, maintaining balanced ecosystems, and even controlling weather patterns to optimize agriculture and mitigate the effects of natural disasters. On a grander scale, a Type 2 civilization extends its energy harnessing capabilities to encompass an entire star system. This might include the creation of massive megastructures like a Dyson sphere, capable of absorbing the vast energy output of its star. With this immense power at their disposal, these civilizations would not only master interplanetary travel, but might also engage in the colonization and terraforming of distant planets and moons. Their technologies could include the ability to manipulate planetary orbits, redirect asteroids for resource extraction or defense, and even harness the exotic energies of phenomena like black holes or neutron stars. At the pinnacle of the Kardashev scale, a Type 3 civilization would control energy on a galactic scale. The technological feats of such a society are difficult to even fathom. These beings could manipulate spacetime itself, achieve interstellar travel, and perhaps even create or destroy stars. With a deep understanding of the cosmos, they might be able to access and utilize the energy of parallel universes, should such realms exist. To our eyes, their technology would appear as magic, an elegant fusion of science so advanced that it defies our comprehension. As we move through these speculative stages, a number of common traits begin to emerge that might define advanced civilizations. Their technologies, for one, would likely operate in perfect harmony with the laws of physics. Such civilizations would have moved beyond crude, destructive forms of energy consumption, achieving sustainability and efficiency at levels that seem almost beyond belief. Furthermore, their survival through the ages, up to the highest echelons of the Kardashev scale, suggests that they have developed social and ethical systems of unprecedented maturity. They would have long transcended self-destructive tendencies like warfare, greed, and exploitation, achieving a delicate balance between technological progress and societal well-being. At the core of their existence, advanced civilizations would likely retain an insatiable curiosity. This drive to explore, understand, and push the limits of knowledge would transcend the boundaries of science, philosophy, and perhaps even physical existence. Should they reach out to communicate with other civilizations, their approach would undoubtedly reflect their superior understanding and capabilities. Whether through seeding life, guiding emerging civilizations, or maintaining the stability of the cosmos against existential threats, their motives would be shaped by a deep sense of cosmic stewardship. In our quest for understanding, one of the most profound implications of this exploration is its impact on our perception of our place within the vast cosmos. As our knowledge grows through advances in astronomy, physics, and cosmology, we are increasingly confronted with the humbling reality of the universe's immensity. With billions of galaxies, each brimming with billions of stars and an unimaginable number of planets, we are forced to confront the stunning vastness of existence. This realization, while overwhelming, also carries with it a sense of profound humility. Our small planet, suspended in the vast void of space, becomes a symbol of both fragility and preciousness, reminding us of the rarity of life and the fleeting beauty of our existence. But it underscores something far deeper: the rarity and preciousness of our existence. It evokes a profound sense of universal stewardship, urging us to preserve the delicate balance of life on Earth. As we look out into the vastness of space, we are reminded that our place in the cosmos is fleeting and fragile, and it calls us to cherish and protect the only home we've ever known. At the same time, our expanding knowledge of the universe fosters an unprecedented sense of unity, a sense that we are not isolated but interconnected with everything around us. The laws of physics, which govern the dance of galaxies and the structure of stars, also influence the smallest particles that make up our daily lives. The very elements that form the stars, hydrogen, carbon, oxygen, are present in every living organism on Earth. This deep, cosmic commonality reveals a profound interconnectedness between all things, from the infinitesimal to the immense. We are not mere observers of the universe. We are an integral part of it, born from the same elements and governed by the same fundamental forces. Our quest to understand the universe is not just an intellectual pursuit. It is a journey that challenges our concept of life itself. The search for extraterrestrial life pushes us to rethink what is possible. Discoveries of exoplanets in habitable zones around distant stars, alongside the study of extreme environments on Earth where life thrives against all odds, suggest that life could be far more abundant and diverse than we once imagined. These revelations invite us to let go of anthropocentric views and consider the possibility of forms of life that may be radically different from our own. Could intelligence exist in ways we can't yet fathom? Could communication with non-human beings alter the course of human history? The study of galaxy dynamics offers a striking example of how interconnected our universe truly is. The interaction between dark matter, the unseen, mysterious substance that makes up the vast majority of the universe's mass, and baryonic matter, the visible matter that makes up stars, planets, and galaxies, is crucial to the formation and structure of galaxies. Though dark matter is invisible and undetectable by conventional means, we know of its existence because of the way it affects the motion of visible matter. Around 85% of the universe's mass is thought to consist of dark matter, and its influence is seen in the way galaxies spin. When astronomers look at the rotation curves of galaxies, they notice something peculiar. Stars far from the center of galaxies do not slow down as expected based on Newtonian mechanics. Instead, they maintain constant or even slightly increasing velocities as they orbit. This anomaly can only be explained by the presence of a large amount of unseen mass, dark matter, that is exerting its gravitational pull on the stars and gas clouds within the galaxy. This mysterious mass creates vast halos around galaxies, stretching far beyond the edge of what we can see, and it is the gravitational influence of these halos that helps keep the galaxies intact. Dark matter doesn't just affect the shape of galaxies, it plays a fundamental role in their formation. During the early stages of the universe, it was the clumping of dark matter that formed the scaffolding around which normal matter, or baryonic matter, could coalesce to create stars and galaxies. This cosmic framework determined the shape and structure of galaxies. Dense clumps of dark matter may give rise to elliptical galaxies, while more extended halos can result in the spiral galaxies we see today. The relationship between dark matter and baryonic matter is crucial for understanding the large-scale structure of the universe. The gravitational pull of dark matter causes matter to cluster in specific regions, creating the cosmic web, a vast, interconnected network of galaxies and galaxy clusters, linked by threads of dark matter and separated by enormous cosmic voids. The study of the intergalactic medium, IgM, the diffuse gas and plasma that fills the space between galaxies, has also revolutionized our understanding of galaxy formation. The IgM is not just a barren void, it is an active and essential component in the evolution of the cosmos. It serves as both a reservoir for galaxy formation and a living record of the processes that shape the universe. One of the most groundbreaking discoveries in recent years has been the detection of the cosmic web, a network of filamentary structures composed of dark matter and gas that stretches across the universe. Through the study of distant quasars, brilliant far-off galaxies, we can observe absorption lines in their spectra, a forest of hydrogen and other elements in the IgM. These absorption lines have revealed crucial information about the temperature, composition, and distribution of the IgM, confirming the existence of the cosmic web and underscoring the dynamic and interconnected nature of the universe. In exploring the cosmos, we are not just seeking knowledge, we are deepening our understanding of our place within the great expanse, revealing the ways in which the universe is far more connected than we ever realized. From the invisible dance of dark matter to the luminous threads of the cosmic web, we are part of a grand, ongoing story, one in which each discovery leads to more questions, more awe, and a deeper connection to the cosmos. But it wasn't until recently that scientists fully realized the pivotal role of the intergalactic medium, IgM, in galaxy evolution. Once seen merely as a passive reservoir of matter, the IgM is now understood to be an active participant in the birth and growth of galaxies. As gas from the IgM is drawn into the gravitational wells shaped by dark matter, it cools and condenses, giving rise to the formation of stars and galaxies. This ongoing process, known as accretion, is fundamental to the formation of cosmic structures. Meanwhile, feedback mechanisms from star formation and active galactic nuclei, regions at the centers of galaxies where energy is expelled back into the IgM, regulate the movement of gas in and out of galaxies. This interplay influences a galaxy's ability to foster new stars, shaping its growth and evolution. Moreover, the discovery of the missing baryons has reshaped our understanding of the universe's matter content. Early studies of galaxies and galaxy clusters showed that only a fraction of the ordinary matter predicted by the Big Bang Theory was accounted for. However, recent observations of the IgM have uncovered the elusive baryons, now identified as the warm-hot intergalactic medium, WHIM. This tenuous, partially ionized gas permeates the filaments of the cosmic web. Although incredibly difficult to detect due to its diffuse nature and the high temperatures at which it emits and absorbs radiation, the WHIM's elusive presence is now being revealed thanks to the advent of advanced X-ray and ultraviolet telescopes. These discoveries are giving astronomers unprecedented insights into the distribution and behavior of these missing baryons, and in turn, the larger structure of the universe. As we peer deeper into the cosmos, the life cycle of stars offers another fascinating window into the forces shaping the universe. The mass of a star is the most significant factor in determining its lifespan and ultimate fate. A star's mass influences the pressure and temperature within its core, dictating the nuclear fusion reactions that fuel it. These processes determine the star's luminosity, its temperature, and how long it will shine. The mass of a star also defines its end. Smaller stars like our Sun may end as white dwarfs, while more massive stars may become neutron stars or even black holes. Stars with a mass up to about 8 times that of the Sun follow a predictable evolutionary path. They spend the majority of their lives fusing hydrogen into helium in their cores. This phase, called the main sequence, is the longest stage in a star's life. But once the hydrogen runs out, the star expands into a red giant and its core contracts, heating up enough to fuse helium into heavier elements like carbon and oxygen. For stars like our Sun, this is where nuclear fusion essentially ceases. As their fuel is exhausted, the outer layers of the star are expelled, creating a planetary nebula. The remaining comes a white dwarf, a dense, hot remnant about the size of Earth, but with a mass similar to the Sun's. Over billions of years, these white dwarfs slowly cool and fade. In contrast, stars with much greater mass experience more violent ends. Once they exhaust their hydrogen fuel, these stars become supergiants, fusing progressively heavier elements in their cores. When they reach iron, however, the fusion process no longer releases energy, but instead consumes it. This imbalance triggers a dramatic core collapse, leading to a supernova, one of the most awe-inspiring events in the universe. In the aftermath, the star's outer layers are expelled, and the core condenses into a neutron star. These neutron stars are incredibly dense, with a mass comparable to the Sun, but compressed into a sphere the size of a city. If the core's mass exceeds approximately 3 solar masses, the collapse results in a black hole, an object so dense that not even light can escape. The boundary around this black hole, known as the Schwarzschild radius, marks the point of no return. Thus, the life and death of a star are intricately tied to its mass. Stars may end their lives in peaceful solitude as white dwarfs or explode in cataclysmic supernovae, seeding the cosmos with the heavy elements needed to form new stars, planets, and possibly even life. The life cycles of stars from birth to death are an essential part of the cosmic cycle of matter, driving the evolution of the universe on a grand scale. In the study of stellar evolution, binary star systems, 2 stars orbiting a common center of mass, offer a unique and insightful perspective. These systems, which make up a significant portion of the stars in the universe, provide a natural laboratory for testing our models of stellar evolution. Observing how one star interacts with its companion can reveal valuable details about the evolution of both stars, especially when one star exerts a significant influence on the other. One of the key phenomena observed in binary star systems is mass transfer. When one star expands into a red giant or supergiant, material from its outer layers can spill over onto its companion, dramatically altering the evolution of the recipient star. This exchange of mass can lead to the formation of exotic objects such as blue stragglers, stars that appear younger than they are, or even create cataclysmic variables and symbiotic stars. Mass transfer in binary systems can allow stars to bypass certain evolutionary stages or speed up their progression, offering new insights into the flexibility of stellar life cycles. Through these interactions, we gain a deeper understanding of how stars evolve, grow, and ultimately shape the universe around them. Binary star systems, especially those involving compact objects like white dwarfs, neutron stars, or black holes, are crucial laboratories for the synthesis of heavy elements. The most iconic example is the merger of 2 neutron stars in 2017, an event that was observed through both gravitational waves and electromagnetic radiation. This historic occurrence confirmed that neutron star mergers are central to the rapid neutron capture process, our process, a nucleosynthesis pathway that creates roughly half of the elements heavier than iron, gold and platinum among them. Likewise, when a white dwarf accretes material from a companion star and reaches a critical mass, it can trigger a thermonuclear explosion, resulting in a type Ia supernova. These supernovae are essential not only for enriching the interstellar medium with iron peak elements, but also for serving as standard candles in cosmic distance measurements. In binary systems, interactions can reveal fascinating scenarios where elements synthesized in one star are transported to the surface of its companion, offering astronomers observable clues about internal processes like dredge-ups and nucleosynthesis. Furthermore, binary systems play a vital role in understanding the end stages of stellar evolution. Observations of systems containing black holes or neutron stars provide valuable insight into the life cycles of massive stars and the conditions necessary for the formation of these dense remnants. The detection of gravitational waves from merging black holes and neutron stars in binary systems has ushered in a new era of astronomy, offering unprecedented insights into matter at extreme densities, the rates of such mergers, and their contribution to the universe's evolution. As we venture further into exoplanetary science, the exploration of exoplanet atmospheres, though still in its early stages, has already begun to reveal an extraordinary variety of environments existing beyond our solar system. Comparing these exoplanetary atmospheres with those of planets in our own solar system is providing valuable clues about the formation, composition, and potential habitability of distant worlds. This comparative approach is vital for understanding the vast diversity of planetary environments and for assessing the possibility of life beyond Earth. Exoplanet atmospheres showcase an impressive range of compositions, temperatures, and weather patterns. Some are akin to those of planets in our solar system, while others are radically alien. For example, hot Jupiters, massive gas giants orbiting very close to their stars, have atmospheres dominated by hydrogen and helium, akin to Jupiter and Saturn, but at such high temperatures that metals within them vaporize. Observations have revealed iron, titanium, and even water vapor in the atmospheres of some of these exoplanets, under extreme conditions that are starkly different from those found in our own solar system. Meanwhile, smaller, rocky exoplanets also show signs of atmospheres capable of harboring water vapor, a crucial ingredient for life as we know it. Yet the diversity in atmospheric compositions is vast, with some exoplanets having atmospheres rich in carbon dioxide or methane, while others, like Mercury or the Moon, lack an atmosphere altogether. The diversity of exoplanet atmospheres offers profound insights into planetary formation and evolution. For instance, the presence of heavy elements and complex compounds in the atmospheres of hot Jupiters suggests a complex history of accretion, perhaps involving interactions with the protoplanetary disk or neighboring bodies in their stellar systems. Similarly, the variations in the atmospheric compositions of rocky exoplanets point to differences in their initial material, their distance from their stars, and their geological activity. When it comes to assessing the potential for life, comparing exoplanetary atmospheres to those in our solar system underscores the importance of atmosphere composition and stability. An atmosphere capable of retaining liquid water, protecting life from harmful radiation, and maintaining a stable climate over long timescales is key. Earth is the only planet in our solar system that meets these criteria, and it serves as a benchmark for identifying potentially habitable exoplanets. The detection of biosignature gases like oxygen, ozone, methane, or nitrous oxide in an exoplanet's atmosphere could indicate biological activity, especially if these gases are found together in combinations that would be unlikely to arise through abiotic processes alone. However, interpreting these signatures is challenging, as some of these gases can also be produced through non-biological processes under certain conditions. Recent breakthroughs in planetary science have significantly reshaped our understanding of planet formation and the diversity of planetary systems. These discoveries, made possible by cutting-edge telescopes and space missions, have unveiled a cosmos teeming with an astonishing array of planets and planetary systems, stretching the limits of our existing theoretical models and opening new frontiers in our exploration of the universe. One of the most striking revelations in recent astronomy has been the discovery of hot Jupiters, gas giants that orbit remarkably close to their host stars, in environments much hotter than those in which gas giants like Jupiter form in our own solar system. Their existence upends traditional models of planet formation, which once assumed that gas giants could only form in the cooler outer regions of a planetary system before migrating inward over time. The mechanisms that govern this migration and the unique conditions under which these planets form and survive in such extreme environments remain active fields of research, urging scientists to rethink their theories of planetary system evolution. Another game-changing discovery has been the identification of super-Earths and mini-Neptunes, planets with no direct counterpart in our solar system. These planets, which lie in mass between Earth and Neptune, present new questions about the processes that dictate a planet's composition and the complex transition from rocky planets to gas giants. The diversity in their size, density, and composition has revealed an astonishing complexity in planet formation that was not anticipated in earlier models, which focused primarily on our solar system's architecture. The detection of planetary systems orbiting binary and even trinary star systems has further deepened this challenge to our understanding. What was once thought to be improbable, the formation of stable planetary orbits in such dynamic environments, is now a proven reality. Numerous planets have been discovered in these complex star systems, forcing us to reconsider the potential for planetary systems to be more resilient and versatile than previously believed. Furthermore, the detection of free-floating planets, those that are not bound to any star and wander freely through the galaxy, suggests that planet ejection from forming or mature planetary systems could be far more common than once imagined. This revelation complicates our understanding of the stability and longevity of planetary systems and raises fresh questions about the forces that drive these planetary ejections. Together, these discoveries are reshaping our understanding of the remarkable diversity of planetary systems throughout the galaxy, prompting astronomers to refine their models, adapt their theories, and incorporate new observations. Our solar system, once considered a standard example, now stands as an outlier among many other strange and unique planetary systems, urging scientists to explore new possibilities in planet formation and system evolution. And then there is the enigma of the dark universe. Dark energy, the mysterious force accelerating the expansion of the universe, constitutes approximately 68% of the cosmos's total energy. Its discovery in the late 1990s through observations of distant supernova has triggered a paradigm shift in our understanding of the universe, sparking new questions about its ultimate fate and the fundamental laws that govern it. The latest theories surrounding dark energy are as diverse as they are fascinating, ranging from modifications of Einstein's theory of general relativity to cutting-edge observational campaigns. One of the leading theories, known as quintessence, proposes a dynamic, evolving field that changes over time and space, contrasting with the static cosmological constant that Einstein initially introduced and later abandoned. Quintessence models suggest that the strength of dark energy may vary over time, potentially explaining why the expansion of the universe is accelerating after billions of years of slow deceleration following the Big Bang. In addition, scientists are exploring theories of modified gravity, which propose that the observed acceleration of the universe's expansion could be due to unknown aspects of gravity not fully accounted for in general relativity, especially at vast cosmic scales. These theories challenge our most fundamental understanding of gravity, compelling rigorous testing through both theoretical models and experimental data. On the experimental side, several ambitious projects are currently underway aimed at probing the nature of dark energy and its effect on the fabric of the universe. One of the most prominent efforts is the Dark Energy Survey, DES, which utilizes a cutting-edge digital camera mounted on a telescope in Chile to map millions of galaxies. By studying the growth of galaxy clusters over time under the influence of dark energy, scientists hope to unveil its true nature. Similarly, the forthcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide unprecedented insights into dark energy over the course of a decade-long survey of the sky, revealing how the universe's expansion has evolved across vast timescales. Another groundbreaking initiative is the Euclid mission, a space telescope developed by the European Space Agency set to launch in the near future. Euclid's primary goal is to map the geometry of the dark universe by measuring the distribution of galaxies and observing the bending of light, known as gravitational lensing, caused by dark matter and dark energy. This will offer valuable clues about the underlying physics that drives the universe's accelerating expansion. Gravitational lensing, a phenomenon first predicted by Einstein, has become one of the most powerful tools in the study of dark matter. This effect occurs when the gravitational field of a massive object, like a galaxy or galaxy cluster, warps the fabric of space-time, bending the light from more distant objects. It can magnify and distort distant light, even producing multiple images, depending on the alignment of the objects involved. Gravitational lensing provides an invaluable means of studying dark matter because it does not emit, absorb, or reflect light, making it invisible to conventional telescopes. Yet the gravitational forces it exerts influence the movement of stars within galaxies, the gas in galaxy clusters, and even the path of light itself. By carefully analyzing the light from distant galaxies and quasars that has been bent by intervening dark matter, astronomers can map its distribution across the universe, even though it remains unseen by traditional methods. These efforts are slowly unraveling the mysteries of the universe's dark and invisible forces, and as they continue, our understanding of the cosmos may soon be on the cusp of another monumental leap forward. There are two primary types of gravitational lensing: strong and weak. Strong lensing happens when the foreground object is massive enough and positioned in such a way that it creates striking distortions or multiple images of the background object. This dramatic effect can lead to phenomena like Einstein rings, where the alignment of a massive lensing object forms a perfect circular image of the light source. By studying these rings and multiple images, astronomers can directly map the mass distribution of the lensing object, revealing vital details about the presence and structure of dark matter. These highly visible effects give scientists a window into the hidden mass that shapes the universe. Weak lensing, however, is subtler, yet more common. It occurs when the distortion of background objects is barely perceptible. Though the changes in shape are slight, this phenomenon affects many distant galaxies, creating a coherent distortion pattern that can be detected over large areas of the sky. By analyzing the shape distortions of millions of galaxies, astronomers can draw detailed maps of dark matter's distribution on cosmic scales, uncovering the web of dark matter that weaves through the visible universe. Gravitational lensing, therefore, has provided some of the most direct and compelling evidence for dark matter, confirming its existence and offering unprecedented insights into its properties. For instance, observations of colliding galaxy clusters, like the Bullet Cluster, have used gravitational lensing to separately map the distribution of both dark and ordinary matter. These observations have uncovered a profound discovery. Dark matter interacts only through gravity, bypassing the other forces that affect normal matter. This crucial evidence further solidifies the dark matter hypothesis, shedding light on the mysterious substance that makes up most of the universe's mass. Now, turning to interstellar phenomena, the discovery of Oumuamua in October 2017 was a milestone that radically altered our understanding of the cosmos. As the first confirmed interstellar object to pass through our solar system, Oumuamua challenged our preconceptions and sparked new avenues of research into the composition, dynamics, and origins of objects from beyond our solar system. Oumuamua, a name that means scout or messenger in Hawaiian, was first detected by the Pan-STARRS 1 telescope in Hawaii as it approached the Sun. Its highly elongated shape, which was unusual for asteroids or comets within our solar system, along with its unexpected acceleration, prompted intense curiosity and debate among scientists. What made this object particularly puzzling was its speed and behavior that couldn't be explained by standard gravitational forces alone. The discovery of Oumuamua is significant for several key reasons. Interstellar visitors. The object confirmed that material from other star systems can and does enter our solar system, providing direct evidence of material exchange between distant stars. This discovery has profound implications for our understanding of planetary system formation and evolution. It suggests that the building blocks of planets, and possibly even the precursors to life, could travel between star systems, carried by interstellar objects. Composition and origins. At first, scientists thought Oumuamua might be an asteroid. However, it lacked the typical cometary tail seen when an object comes close to the Sun, which puzzled astronomers. Some suggested it could be a new type of object, possibly a fragment from a disintegrated comet or a piece of interstellar debris. Understanding its composition and origins could provide key insights into the processes that occur in other planetary systems and the variety of objects that form in those distant environments. Moreover, Oumuamua exhibited non-gravitational acceleration, meaning its speed and trajectory were altered in ways that couldn't be explained by the Sun's gravity alone. This led to numerous hypotheses, such as outgassing, the release of gas from the object's surface. While this is a common phenomenon in comets, no visible coma or tail was seen in Oumuamua, making the acceleration even more mysterious. This behavior has ignited ongoing discussions about what forces might be at play in such interstellar objects. Then came 2I Borisov, another interstellar marvel discovered in August 2019 by amateur astronomer Gennady Borisov. As the second interstellar object detected passing through our solar system and the first confirmed interstellar comet, Borisov marked another significant moment in our exploration of the cosmos. Unlike Oumuamua, whose origins sparked a flurry of debate, Borisov was quickly identified as a comet, thanks to its unmistakable cometary features, a glowing coma and a tail. These features are characteristic of comets when their icy bodies begin to sublimate as they approach the sun. Each of these discoveries deepens our understanding of the universe, revealing how objects from other star systems can shape our knowledge of the cosmos. Borisov offered scientists an extraordinary chance to delve into the material composition of an object from another planetary system. Observations revealed that its composition closely resembles that of comets native to our own solar system, providing compelling evidence that the processes responsible for the formation of comets might be universal. This insight is invaluable, opening doors to a deeper understanding of the fundamental building blocks of planetary systems and shedding light on the distribution of water and organic molecules across the cosmos, elements that are critical for life as we know it. The trajectory of Borisov further confirmed its interstellar origin, entering our solar system with a hyperbolic orbit that indicated it was not bound by the sun's gravity. Its incredible speed and the path it traced through our system offered crucial data about its approach and eventual departure, contributing to our understanding of the dynamics of interstellar objects and the gravitational interactions that govern our solar system. The implications for planetary system formation are profound. The discovery of Borisov, coming so soon after the discovery of Oumuamua, suggests that interstellar objects passing through our solar system may be far more common than we once thought. This revelation supports the idea that material exchange between planetary systems in our galaxy could play a crucial role in the evolution of these systems, and potentially even in the seeding of life-sustaining compounds across the galaxy. The observations of Borisov highlight the pressing need for continued vigilance and the development of advanced technologies to detect and study such interstellar visitors. With the rapid advancements in telescope technology and global observation networks, astronomers are hopeful that even more interstellar objects will be discovered, offering new insights into their origins, trajectories, and physical properties. Each new discovery brings us one step closer to piecing together the larger puzzle of our universe's history, the processes that govern the formation of planetary systems, and the broader dynamics of the cosmos. Hoag's object is a captivating enigma, a galaxy unlike any other. With its nearly perfect circular ring of young, hot blue stars surrounding a compact, brighter yellow core of older stars, Hoag's object defies traditional expectations of galactic structure. Classified as a ring galaxy, it presents a striking and rare configuration that continues to baffle astronomers, challenging existing theories about galaxy formation and structure. Discovered in 1950 by astronomer Arthur Hoag, who initially mistook it for a planetary nebula, further research revealed its true galactic nature. Situated approximately 600 million light-years away, Hoag's object stands out as one of the most well-defined examples of a ring galaxy, an extremely rare class of galaxy in the observable universe. The origins of Hoag's object's distinctive ring structure remain one of the most debated topics in modern astronomy. One theory suggests that it could have formed as the result of a unique type of galactic collision or merger, where a smaller galaxy passed through the center of a larger one, triggering a burst of star formation that eventually shaped the iconic ring. Alternatively, the ring may be the result of a unique instability within the galaxy's original disk, which rearranged itself into the present ring-like structure. Even more intriguing is the discovery of a second, fainter ring just outside the primary one, hinting that the galaxy's history is even more complex than previously imagined. This outer ring, composed of faint, older stars, suggests periodic episodes of star formation or perhaps multiple galactic events that have contributed to Hoag's object's current enigmatic structure. Zombie stars are one of the cosmos's most perplexing phenomena, challenging our traditional understanding of stellar life and death. In astronomical terms, a zombie star refers to a stellar remnant that has survived a supernova explosion, an event typically believed to signify the death of a star. Remarkably, these stars continue to shine after the explosive event, suggesting that the supernova process was either partial or failed altogether. The result is a surviving core that persists in emitting light, defying the conventional notion of stellar death. These resurrected stars represent a fascinating anomaly in the life cycle of stars, offering new insights into the ways stars can evolve and persist in the face of what should have been their end. The concept of zombie stars emerged as a result of observations that defied the expected outcomes of certain supernovae. Among these anomalies, Type 1a supernovae stand out. These thermonuclear explosions of white dwarfs in binary systems are crucial tools in measuring cosmic distances and have played a pivotal role in uncovering the accelerating expansion of the universe. Yet, some observed supernovae are dimmer than the standard Type 1a explosions, indicating that the white dwarf was not entirely obliterated. Instead, it appears to have lost a significant portion of its mass during the explosion, leaving behind a smaller, damaged remnant. This phenomenon has sparked the idea of zombie stars. The existence of these damaged remnants has profound implications for our understanding of stellar evolution and the various mechanisms that govern supernovae. It suggests that the final stages of stellar evolution are more complex than previously thought, influenced by a variety of factors, including the star's mass, composition, and its interactions with companion stars in binary systems. These observations challenge simple categorizations of stellar life cycles and emphasize the intricate physics driving supernova explosions. Zombie stars, therefore, present a rich field of study, offering insights into the conditions necessary for different types of supernovae to occur and the processes that lead to partial destruction of stars. This research has the potential to refine our understanding of nucleosynthesis, the creation of heavy elements in supernova explosions, because zombie stars might provide unique environments where these processes unfold differently compared to complete supernovae. Furthermore, studying these remnants can help improve models of Type 1a supernovae, which are crucial for cosmology. These supernovae act as standard candles for measuring cosmic distances. Understanding any deviations from the norm, like those introduced by zombie stars, is essential for ensuring the accuracy of measurements that shape our comprehension of the universe's expansion. Meanwhile, the mysterious behavior of KIC 8462852, or Tabby's star, has captured both the imagination of astronomers and the curiosity of the public. Situated about 1,470 light-years away in the constellation Cygnus, this star has exhibited erratic dimming events that have baffled scientists since its discovery. These dimming episodes are unlike anything observed in other stars, leading to a wide array of theories and speculations about their cause. Tabby's star was first brought to attention by citizen scientists working on the Planet Hunters project, which uses data from the Kepler Space Telescope to identify exoplanets by detecting the characteristic dips in starlight caused by planetary transits. However, the light pattern from KIC 8462852 stood out. Its brightness would dip by as much as 22%, and the events showed no predictable patterns typically linked to planetary movement. The irregularity and depth of the dimming couldn't be explained by known astronomical phenomena, prompting further investigation. Several theories have been put forward to explain the behavior of Tabby's star. One suggests that a swarm of comets or debris orbiting the star might occasionally block its light. This could occur if a nearby star disturbed a comet belt, sending a large number of comets into paths that align with Earth's view of the star. However, the sheer volume of material needed to cause such substantial dimming makes this scenario seem unlikely. Another theory proposes that the dimming could be caused by dust clouds, created by the collision or breakup of asteroids or planets in the star's vicinity. The resulting debris could intermittently obscure the star's light, accounting for the irregularity of the dimming events. Yet, this explanation would imply an extremely rare and coincidental timing for such an event. Perhaps the most speculative, and certainly the most controversial hypothesis suggests that the dimming could be caused by an alien megastructure, such as a Dyson sphere, designed to capture the star's energy for use by an advanced civilization. Although this idea has sparked imaginations, most scientists dismiss it as highly improbable, viewing it more as a reflection of the enigma surrounding Tabby's star rather than a serious explanation. Still, it stands as a symbol of how the mysteries of the universe often leave room for wild, yet fascinating, speculation. Hypervelocity stars, the celestial sprinters of our galaxy, streak through the Milky Way at mind-boggling speeds, fast enough to break free from the galaxy's gravitational grasp. These stars race across the cosmos at velocities surpassing hundreds of kilometers per second, far faster than ordinary stars like our Sun. Their study has opened a window into some of the most dynamic processes at play within our galaxy and the immense forces capable of hurling stars across vast distances. Although the existence of hypervelocity stars was initially a theoretical concept, their first detection didn't occur until 2005. Since then, advances in observational technology have revealed more of these stellar outliers, each one offering a unique glimpse into the violent and mysterious phenomena that fuel such incredible velocities. The leading theory explaining their origin centers on the supermassive black hole lurking at the heart of the Milky Way. A binary star system, two stars locked in an orbit around each other, may wander too close to this black hole. The intense gravitational forces of the black hole can tear the binary system apart, capturing one star and flinging the other out at a speed so great that it escapes the galaxy entirely, embarking on a lonely journey through intergalactic space. In addition to interactions with the black hole, other scenarios, such as star system collisions or the explosion of a star in a binary system, could also produce hypervelocity stars. Though rarer, these events add variety to the hypervelocity stars observed across the universe. The study of these stars has profound implications for astrophysics. By tracking their velocities and trajectories, scientists can gain crucial insights into the galaxy's mass distribution, including its elusive dark matter halo. Moreover, these stars serve as cosmic probes, offering a peek into the extreme environment surrounding the galaxy's central black hole. Their movements help map out the gravitational potential of the Milky Way, contributing to our understanding of one of the most enigmatic regions in the universe. Meanwhile, luminous red novae, LRNE, present a rare and fascinating chapter in stellar evolution. These cosmic explosions are marked by their striking red hue, transient nature, and luminosity, which lies between that of a classical nova and a supernova. Their study has captured the attention of astronomers eager to uncover the underlying mechanisms of stellar evolution and interaction. LRNE are believed to arise from the merger of two stars in a close binary system. When the stars are close enough, material from one star can be siphoned off by its companion, eventually leading to a merger. The tremendous release of energy during the merger causes a brilliant outburst, accompanied by an expanding shell of gas and dust, giving the nova its signature red glow. This process offers key insights into the final stages of stellar evolution and the intricate dynamics of binary star systems. One of the most well-known examples of an LRN is V1309 Scorpii, which erupted in 2008. Prior observations of this system provided a rare opportunity to study the pre-merger history, revealing how the binary star's orbital period steadily shrank as they spiraled closer together. This event has since become a cornerstone for understanding the mechanics of LRNE. LRNE not only expand our knowledge of transient cosmic phenomena, but also deepen our understanding of binary star systems and the dramatic events that shape their destinies. Magnetars, among the most extreme and captivating objects in the cosmos, are a unique and powerful subset of neutron stars. Their significance stretches beyond the mere observation of strange celestial bodies. They offer profound insights into the fundamental processes of stellar evolution and the formation of some of the universe's heaviest elements. These enigmatic stars are the remnants of massive stellar giants, their cores compressed after the violent cataclysm of a supernova explosion. What sets magnetars apart is not just their immense density, but their intensely powerful magnetic fields, which are among the strongest known in the universe, thousands of times stronger than that of a typical neutron star. The intense magnetic fields of magnetars can exceed 10 Gauss, a strength so vast it could distort the very fabric of space around them. To put this into perspective, Earth's own magnetic field is only about 0.5 Gauss, an almost negligible fraction by comparison. But how did these extraordinary magnetic fields come into being? Scientists theorize that the immense strength of these fields is the result of the conservation of magnetic flux during the collapse of the progenitor star. As the star's core collapses into a neutron star, its magnetic field lines are compressed into a tiny volume, amplifying their strength to cosmic extremes. Yet, the real wonder of magnetars lies in their extraordinary behavior. These stars are notorious for releasing violent bursts of energy, emitting high-energy X-rays and gamma rays at levels that can be felt across vast distances, disturbing the very atmosphere of our own planet, despite the magnetar being thousands of light years away. These outbursts, including giant flares and energetic bursts, are thought to arise from the instability in the magnetar's magnetic field, which can suddenly realign, releasing vast quantities of energy in the process. Such phenomena not only provide a window into the extreme physics at play, but also challenge our understanding of matter under conditions of extreme density and magnetic intensity. Through the study of magnetars, scientists are able to probe the limits of known physical laws. These observations are crucial for understanding the behavior of matter in extreme environments and even have implications for the study of gravitational waves, ripples in space-time caused by violent cosmic events. Magnetars may also offer clues to the nature of subatomic particles and the forces governing them in ways that are impossible to replicate here on Earth. Their connection to other astronomical phenomena, such as short gamma-ray bursts and anomalous X-ray pulsars, further expands our understanding of the vast and varied outcomes that arise from the death of stars. In the broader context of stellar evolution, Wolf-Rayet stars represent another chapter in the life of massive stars, demonstrating some of the most dramatic and explosive processes in the universe. These stars, named after the French astronomers Charles Wolf and Georges Rayet, who first identified them in 1867, are characterized by their violent stellar winds and massive loss of outer material. As they evolve, they shed their outer hydrogen layers, exposing the heavier elements in their cores. Elements like carbon, nitrogen, and oxygen that are key to the process of chemical enrichment across the universe. Massive, often over 20 times the mass of our Sun, Wolf-Rayet stars are in the final stages of their life cycle, losing mass at a staggering rate. The intense radiation pressure from their cores pushes their outer layers into space, enriching the interstellar medium with the heavy elements required to build new stars and planetary systems. Their remarkable mass loss plays an essential role in the galactic chemical evolution of the universe, laying the foundation for the creation of future generations of stars and planets. Interestingly, these stars are often located in regions of active star formation, and they are frequently considered precursors to certain types of supernovae, particularly the type 1b and IC supernova, which are defined by the absence of hydrogen lines in their spectra. The end of a Wolf-Rayet star's life is marked by a spectacular, explosive death, a supernova that can leave behind either a neutron star or a black hole, depending on the star's remaining mass. These cosmic giants, both magnetars and Wolf-Rayet stars, are not merely fascinating objects of study. They are pivotal to our understanding of the universe. Their violent deaths and extraordinary characteristics provide insight into the fundamental forces that shape the cosmos, revealing mysteries that continue to challenge and expand the frontiers of modern astrophysics. In some instances, the catastrophic collapse of a Wolf-Rayet star can give rise to long-duration gamma-ray bursts, the most energetic events known in the universe. These bursts, detectable across immense cosmic distances, illuminate the mysteries of the universe's most powerful forces. As we journey deeper into these enigmatic phenomena, we encounter something equally awe-inspiring: the Fermi bubbles. Fermi bubbles are vast, balloon-shaped structures teeming with high-energy particles that emerge from the heart of the Milky Way. Stretching approximately 25,000 light-years above and below the galactic center, these enigmatic bubbles were first discovered in 2010 through the observations of NASA's Fermi Gamma Ray Space Telescope. Radiating in gamma rays, the highest energy form of light, These bubbles challenge our understanding of the cosmic processes that shape our galaxy. Though their discovery has unlocked valuable insights into the workings of the Milky Way's core, the origin of the Fermi bubbles remains a subject of heated debate among astronomers. One prevailing theory suggests that the bubbles were created by explosive eruptions from the supermassive black hole at the heart of our galaxy, Sagittarius A Star. These eruptions, which could have occurred millions of years ago, may have been triggered by the black hole consuming vast amounts of gas and dust, releasing immense amounts of energy that sent particles speeding into space, thus forming the bubbles. Another hypothesis posits that the Fermi bubbles could be the aftermath of intense star formation activity near the galactic center. In this scenario, massive stars would have detonated as supernovae, unleashing powerful waves of energy that shaped the surrounding space and contributed to the formation of the bubbles. These stellar explosions would have accelerated particles to nearly the speed of light, fueling the gamma-ray emissions observed. The study of Fermi bubbles is of paramount importance for several reasons. Not only do they serve as a historical record of the Milky Way's energetic past, offering vital clues about the events that have shaped our galaxy's evolution, but they also provide a deeper understanding of the dynamics of supermassive black holes and their role in the evolution of galactic nuclei. Investigating the energy sources that power these bubbles may reveal much about the forces that govern the universe on a grand scale. Moreover, the particles contained within the Fermi bubbles are thought to contribute to the creation of cosmic rays, high-energy particles that travel through space at nearly the speed of light. Understanding these cosmic rays and the mechanisms behind their acceleration is crucial to unlocking the mysteries of their origins and their potential impact on our galaxy. The Fermi bubbles also present a fascinating glimpse into the types of large-scale structures that exist in galaxies. Observations of similar bubble-like phenomena in other galaxies suggest that the processes shaping the Milky Way may not be unique. These structures offer a comparative tool for astronomers to study and better understand the cosmic forces at play in distant galaxies. Shifting focus from the bubbles, we turn to the theoretical wonder of wormholes. Rooted in the equations of Albert Einstein's general theory of relativity, wormholes offer the tantalizing possibility of connecting distant regions of space and time, potentially enabling travel across vast cosmic distances in a fraction of the time it would take light to traverse such distances in normal space. The term wormhole was coined by theoretical physicist John Archibald Wheeler in the 1950s, but the concept traces its origins back to a 1935 solution of Einstein's equations, jointly proposed by Einstein and Nathan Rosen. These Einstein-Rosen bridges, as they were originally called, were envisioned as pathways that could link two disparate points in space-time and possibly even connect two entirely different universes. The most common depiction of a wormhole is that of a tunnel, with two ends situated in separate points of spacetime, similar to a tunnel that connects two distant cities. However, while the theoretical potential of wormholes is vast, they remain one of the most elusive and intriguing concepts in modern physics, offering a glimpse into a future where the boundaries of space and time might no longer constrain our imagination. And so, the interior of a wormhole might be a region of space-time that allows a traveler to journey from one end to the other faster than light can travel outside its bounds, though it wouldn't technically exceed the speed of light within the wormhole itself. But despite this compelling theoretical framework, there is as yet no empirical evidence to suggest that wormholes exist or that they could be harnessed for space travel. One of the most formidable obstacles lies in the stability of wormholes. Theoretical models predict that the throat of a wormhole would collapse almost instantly, preventing anything from traversing its length. To keep such a structure open, exotic matter with negative energy density would be necessary, yet this kind of matter has never been conclusively observed. This exotic matter would counterbalance the wormhole's natural tendency to collapse, but questions remain. Can such matter exist in sufficient quantities? And if it does, could we manipulate it to keep a wormhole stable? These questions, for now, remain speculative. Moreover, even if wormholes could be stabilized, navigating them presents yet another challenge. There would be no guarantee of where or when the other end would open, making it a risky proposition for anything beyond theoretical exploration. The concept of wormholes, however, holds profound implications for our understanding of the universe and the nature of space-time itself. It pushes the boundaries of our conventional understanding of distance and connectivity, suggesting a universe far more intricate and interconnected than we ever imagined. Wormholes also raise tantalizing possibilities for time travel. If they could exist, they might not just offer shortcuts across space, but also allow travel through time, opening up questions of causality and temporal paradoxes. As we near the end of our exploration of the vastness of astronomy and cosmology, one thing becomes clear. These discoveries have profound philosophical ramifications, influencing how we understand existence itself and our place in the cosmos. The more we uncover about the universe, the more we are challenged to rethink our perceptions of significance, identity, and unity. Recent breakthroughs, from the detection of gravitational waves to the first ever image of a black hole's event horizon, expand not only our knowledge of the physical universe, but also provoke deeper reflections on the nature of reality itself. Gravitational waves, for example, have validated Einstein's century-old prediction, opening up new avenues for studying the universe's most cataclysmic events. This discovery emphasizes our profound connection to the cosmos, as we are now able to hear the ripples in space-time caused by distant astrophysical phenomena. The imaging of a black hole's event horizon, a feat once considered impossible, further stretches the limits of human imagination and scientific achievement. This monumental breakthrough does not merely confirm the existence of these enigmatic objects, but also serves as a humbling reminder of the vast mysteries of the universe that remain to be uncovered. It is a testament to our relentless pursuit of knowledge and the power of collective human endeavor. The exploration of exoplanets and the ongoing search for extraterrestrial life have revolutionized our philosophical perspectives on existence. The discovery of worlds orbiting distant stars within habitable zones, where life, as we know it, could potentially thrive, challenges our sense of Earth's uniqueness and encourages us to consider the possibility of life beyond our planet. This search expands our understanding of the potential diversity and resilience of life, reminding us that we may just be one among many expressions of life in an overwhelmingly diverse universe. The multiverse theory, suggested by some cosmological models, proposes that our universe may be only one among countless others, each with its own set of physical laws. While still highly speculative, this idea shakes the very foundations of our philosophical outlook, prompting us to question the nature of reality itself and our place within it. It challenges the conventional view of a singular universe, urging us to envision a far grander, more varied cosmic landscape than we ever dared to imagine. What mysteries do you believe still lie hidden within the universe? From the elusive dark matter and dark energy that shape the structure and expansion of the cosmos, to the captivating idea of parallel universes and the enigmatic nature of black holes, where the laws of physics break down in mind-boggling ways, our quest for understanding has only just begun. And with every discovery, a new layer is peeled back, uncovering not just answers, but an endless cascade of questions, each more profound, more curious than the last. What do you think? What ideas or insights have you gathered from this journey? Share your thoughts in the comments below. Thank you for joining us, and don't forget to subscribe to Starflux for more captivating explorations just like this one.